This conference will now be recorded.
Can you all hear me?
Yes.
Okay.
Yep.
Hi. Good morning, everyone. I'm speaking from Miami, Florida, and I really appreciate all the speakers and attendees who joined this conference, or we can call it a workshop, Coastlines and People conference. I want to acknowledge the funding from the National Science Foundation. And originally this was going to be an in-person workshop in Miami, but unfortunately because of the COVID situation, we had to make it a virtual conference, which works well. We have, about 140 registered attendees for this. And also we were looking for a software platform for the virtual conference that works. And we decided on the GoToMeeting because that's the one that will work for everybody. Many federal participants could not use Zoom, as I understood. So I hope that works well. Anyway, so the whole, I'll talk about the objectives of the workshop in a minute, actually in this slide. There are three objectives that we identified for this workshop or conference. First one is to understand the interaction of biophysical, social, behavioral, and economic systems in coastal regions. We believe that you have a complex system of systems, including biophysicals, social behavioral aspects in coastal region, and also the economic systems. So we tried to assemble a group of actually 17 speakers to cover these three topics, and I'll talk about the schedule in a minute. We have interaction within each system, like the biophysical, but I think more importantly, there are interactions between the other systems, like social, behavioral, and economic system. We also wanted to identify new data gaps that could be addressed by non-governmental, local, regional, and federal networks, with the idea of formulating an ideal coastal observatory to understand and model these systems together. And finally, the interoperability requirements of data and models. We typically model one system, and within that we may have several models that interact within itself. But we really rarely talk about, what are the data and modeling requirements across these systems. So that's the goal. We have about, like I said, 17 speakers who are experts in various aspects of these topics. We have very short talks, about 15 minutes. If we have time within that 15 minutes, we'll allow attendees to ask questions. So I just want to recognize the organizing committee of the workshop. We have the first four you see on the left. These are the folks who actually joined together to write the NSF proposal, originally to hold the workshop. That was last year, maybe even earlier. With myself at the PI, and then I have Sparkle Malone, Michael Sukop, Tiffany Troxler. They are also going to be moderating this workshop, and they are all from the Florida International University. And there we have others who are, locally and nationally active on these topics of coastal issues, sea level rise, and also monitoring, and also some non-governmental organizations like Miami Foundation, Catalyst Miami, and Clio Institute. So I want to recognize their support and collaboration. So just to get things moving, there's a little bit of some logistics I think I should mention up front. If you're not speaking, please mute yourself. but we may mute everyone at the beginning, particularly the panelists and speakers, and especially the attendees. And that was to avoid any unnecessary noise coming through. But during the Q&A, you know, you can unmute yourself, or we will unmute you. If you have a question of during the Q&A session, the easiest thing might be to type Q question mark in the chat box, and then the moderator will see you and then unmute you to ask the question. And we may have to select some questions since we don't have a whole lot of time for Q&A, but we have, you know, a couple of slots where we can open up for a question that we may miss. If you are a speaker, please leave your camera on if that is possible. And also audience members, when you ask questions, you may also want to leave the camera on. For the speakers, to keep the time of the conference on schedule, we have a couple of folks who will actually play a ringtone from a phone, a small, a soft ringtone that will give you a notice around 13 minutes. So that you have an idea how much time is left. But I'm hoping you will kind of manage your time yourself. With that, I just want to show you this website also that we have. Unfortunately, we don't have time to introduce all the speakers and their bios, but we'll add them to the website. So this website has a schedule. You know, our keynote speaker, our institute director, Todd Crowell. Again, we are from the Sea Level Solutions Center in the Institute of Environment at FIU, and he's the director. And then each session will be moderated by one of us, and then we have identified some speakers for each session. Session 1 on what we call behavioral and social science, observations and models. Session 2, Mike will moderate that, and we have 3 speakers on economic observations and models. And then session 3 will be moderated by Tiffany and Sparko. And it's a fairly long session. It's on biophysical observations and models. Obviously, we could have a lot more to cover these topics, so we didn't have enough time. We decided not to have multiple day conferences, although we might rethink that later on if there is enough interest. Then finally in session 4, it's about 1 hour, 15 minutes long to have a good plenary discussion that I'm hoping all of you will stick around to have a good discussion on what does that interoperability of models mean and data mean, and what do we need to do to make that happen. So with that, I didn't get the ringtone. That means I'm on time. Let's go to Todd, who's our keynote speaker. Let me see if he can come on. Todd, are you there?
Todd may be having some technical difficulties. He was in the middle of a windstorm and his power just went out, so he's trying to figure out whether he can use his hotspot and call in. So we may give him a couple minutes to see if he can.
Yeah, we got a couple of minutes left in and he also has 3 minutes left. Let me make sure other speakers are on in here. Let me see if Christopher Emmerich, are you there?
I am here.
Hi, Christopher, thank you. Let me make Sam Brody, are you?
I'm here.
Oh, thank you, Sam. Great. And Jonathan Gilgan?
Yes, I'm here.
Great, thank you, Jonathan. And Ali Mustafawi? He's in Texas. So I'm hoping he will arrive later. I don't hear him yet. I don't see him yet on the list either. Let's see. Let me go down the list. Well, we have a little bit of time for session 2. So
Obi,
I
do
can-
you want to mention the survey and any of the questions?
Yes, thank you, Tiffany. If you, if you, in my email that I had sent out, we had, maybe, am I still sharing? I guess so.
Yeah.
So we also decided to have a survey. This was sent out to all the speakers and attendees. And the idea is to gather information that we cannot cover in a one-day conference like this. Your email address, your name, if you're using any models, what are you using? What category of models you're using? And what are the inputs and outputs? And limitations of data gaps and primary techniques that you are using, for example, hydrodynamic modeling or ecological modeling or water quality modeling, and spatial and temporal domains. And the last questions are targeted to identify these interactions among models. And what do you think about, your models support these other disciplines, the behavioral and economic models? Any input on that will be useful. We are required to write a report on this at the end. So it would be very valuable if you can send it to us maybe right after the workshop. Let me see if we start back in. Tiffany, are you?
I haven't heard anything yet.
Yeah. So for everyone's benefit, Todd Kroll, who is our first speaker, he's in Utah, and apparently there is a big snowstorm over there, or some kind of storm. His power went out. He's trying to join in. We still have, we can wait a couple of minutes. Yeah, okay. Yeah, if we don't have any technology issues, that's nowadays, that will be very unusual. I'm glad many of our speakers are on the list already. We have about 70 people on the list already. Let's see. If I'll give another minute or two. If not, we can start with Christopher and then come back to Todd when he's back online. Always. Let's see. I guess I did not count on having no power for anybody. But
Yeah, nothing yet.
okay. So why don't we go ahead with the first speaker, and right after, that talk from Christopher Emmerich, we will get back to Todd. So let me, if that's okay with everybody. So we are getting into the session 1, behavioral social science observations and models. We have 4 speakers. The first speaker is from Christopher Emmerich, University of Central Florida. And then, by the way, I don't have time to describe what your background and all that is. So for the interest of time, he's going to talk about the hazard vulnerability science, from background to metrics to models and measurements. So Christopher, you want to share your screen and get started? Then.
Sure, thanks a lot, Obi. Thanks, everyone.
Okay.
Here we go.
Yeah.
Let me know if you can see my screen. I need to turn some things off.
We can, if you can, yeah, it's a full screen. Yeah, that's good.
Just trying to move the whole sidebar that's covering half of my screen right now.
Okay.
Can you see just the presentation or everything else as well?
We see other things as well.
Okay, let's see. Can't leave the meeting.
Actually, I think the presentation is dominant.
Yeah, that can work, I think.
Yeah,
Okay,
it's really good. Yeah.
Perfect. Good morning, everyone. My name is Chris Emmerich. I'm an associate professor at the University of Central Florida, and I'm trying to advance my slides. There we go. I received my PhD in 2005 under the tutelage of Susan Cutter at the University of South Carolina, but I haven't always been an academic. I have worked for FEMA, I've worked in the private sector. I am going to, as Obi indicated, attempt to tell you everything there is to know about hazard vulnerability science in the next 14 minutes now. So those of you that remember possibly the movie Matrix, what's going to happen over the next few minutes is effectively like Neo, you're going to learn Kung Fu because I'm just going to throw everything at you and then we'll figure out what sticks later on. I'm a hazard vulnerability guy. So I study everyone's bad days and try to make the next day better. And today I'm going to talk to you a little about how we can include social vulnerability science to support more robust coastal science. So when we think about social vulnerability, and I'll talk to you about how it manifests in a few minutes, what really makes it stick is that we can identify people and characteristics of people and turn them into numbers so that we can map them and analyze them in relation to other things. So by understanding social vulnerability, we can better account for disproportionate impacts through this lens of equity. We can build better plans and programs and policies if we have a more clear understanding of that differential vulnerability in relation to climate sensitive hazards. And so what you see here in these first two images are bivariate maps of social vulnerability and different outcomes. These two maps specifically look at FEMA data and FEMA applicant data following Hurricane Maria and Hurricane Irma. But rather than understanding just where you had more FEMA applicants or more FEMA damage, what these maps allow you to do is understand where you have high amounts of FEMA applicants or high amounts of damage in association with high social vulnerability, effectively enabling the targeting of scarce disaster recovery resources in these disasters. And I would contend that using a representative picture of vulnerability can help lead to the most appropriate local solutions. And this last map you see here is a social vulnerability index of just Michael impacted areas, Hurricane Michael impacted areas. And we'll get into a little bit about social vulnerability and how it manifests itself differently across the landscape. But I wanted to just couch everything we're going to talk about in this concept of if we don't understand our vulnerable populations, and then if we don't overlay what we understand about vulnerabilities in reference to biophysical or other impacts, then we're missing the picture and probably not able to come up with the most appropriate local solutions. Interestingly, there has been massive growth in the interest in social vulnerability. This is a quote from HUD, which came out from an RFP just a little while ago, specifically calling out the field of social vulnerability science and then the social vulnerability index, of which I know a little bit about. So what it's coming down to, and you maybe have read the news about what's happening in Houston and where entities are actually using vulnerability measures to make critical decisions about distribution of money or plans or policies or programs. And so social vulnerability and different models of social vulnerability are starting to become very important. They have been used by many entities, and you can see some of the entities that are using the social vulnerability index listed here, including Surging Seas, NOAA's Digital Coast. The forthcoming National Risk Index uses the social vulnerability index. So many people are using vulnerability models, and I think it's really incumbent upon vulnerability scientists to make sure that they're used in appropriate ways. So when we talk about social vulnerability, what are we talking about? Well, we're talking about a relatively new and young field of research. Started probably the first social vulnerability article I ever read was 1970, and it was the vulnerability of Indianapolis. And it was actually the first principal components analysis I ever saw. But up through the early 2000s and finishing with the Cutter et al. Social Vulnerability Index to Environmental Hazards, there was a substantial amount of literature on case studies of vulnerability and pinpointing those things that made people less able to prepare for, respond to, or rebound from disaster events. And understanding these things conceptually and then empirically helps us better understand where we can create interventions that work. But what you'll notice here with this graph is that since 2003 and the Cutter et al. Social Vulnerability Index paper, there has been many articles, and that's indicated by this orange line, about social vulnerability. As a matter of fact, there's been more than 1,000 case studies identifying vulnerable populations. The great thing is that the case studies and all the papers that have happened since 2003 are only strengthening the previous literature that we have identified and can identify those characteristics of populations that make them less able to prepare for, respond to, and rebound from disasters. So current vulnerability science is really aimed at improving on the measures that are there, not replacing them, just making them better. So what we do know about social vulnerability is a lot of things that folks would say, yes, of course, that we know that, right? We know that special needs populations are more vulnerable, that the old are more vulnerable, and that the young are more vulnerable, that the rich are less vulnerable than the poor. And at the surface, we can understand these things. What's beautiful when you get into a mapping application of social vulnerability is that we can understand these things for everywhere, and we can understand how vulnerability manifests itself differently across the landscape. So let me talk to you about some of the things that go into the Social Vulnerability Index. We have 6 pillars of vulnerability: employment structure, housing, population structure, race and ethnicity, socioeconomic status, and special needs that you see on the left here. And we have currently 29 different socio-demographic variables that go into the Social Vulnerability Index that we put into these pillars. But let me start by saying I have an article under review right now that says these pillars are not representative. So empirically and statistically, we're measuring something different than we are theoretically and conceptually. So in this way, vulnerability science is, I don't want to say part science and part art, but what is statistically proven is not necessarily what it has been conceptually proven in the literature. So we take all these things and we put them into a principal components analysis, and we could have a whole other talk about what principal components analysis does, but effectively it groups variables based on their correlation to a concept. And what it comes down to in the end is we can describe vulnerability both as a table in which we have influences of vulnerability, the variables driving that influence, and then the correlation with the component, or we can do it as a map. And I would argue that the map looks better. So on the right-hand side, we see the map here of social vulnerability for every census tract in the United States, where we can start to see some fairly clear patterns of high social vulnerability versus low social vulnerability. But then I would argue that a map of the whole United States is not useful because all disasters are local and many solutions are local. So we want to quickly move away from a whole US map and then dive down deeper into other things. So how can SoVI help inform you? And here's just a breakdown for the Southeast United States of counties based on social vulnerability. So understanding our social vulnerability, we can first start to understand how your state or county or community measures up. So we can see, for example, in Arkansas, we only have 2 counties with high social vulnerability, but 21 counties with medium high social vulnerability. And we can see different patterns across the landscape in this regard. But what really is interesting is, are your socially vulnerable places coincident with hazardous places? And I would argue that this is where vulnerability really matters. It's like a tree falling in the forest, right? If you're vulnerable but you have no risks, then there's a different set of mitigation strategies than if you have risks but not vulnerability. So this is why vulnerability and understanding vulnerability becomes really important. So when we start accounting for risks, we start to get a better understanding. This map in the foreground was supposed to come up later, shows social vulnerability in reference to peak ground acceleration. So without the peak ground acceleration map, you might make a different set of decisions on how to mitigate the hazards. But now once you understand, again, overlaying that hazard information, that the peak ground acceleration is greater in the northeast than the southwest, that might lead to a different set of planning or intervention decisions. I've also done some work with Oxfam. What you see here is a bivariate map of social vulnerability to multiple hazards across the southeast United States. So here you can really start to understand that place matters. And if we were going to be using scarce resources, or in this case, in the case of CoPe, focusing on specific places, this map might help us understand which places need more research and solutions than other places. So when we turn social vulnerability data into map data, site and situation become more clear. And finally, this is a case study was for Presidential Disaster Declaration 4277, where we were trying to help Louisiana make better decisions about, again, using those scarce resources. So whereas you look at this last map and we see that Louisiana, specifically Orleans Parish, is high, right? And in the southeast Louisiana, we have a decent amount of high vulnerability and high impacts. When we look deeper, we see that, well, it's really more nuanced when we understand more deeply about the spatial nature of those impacts and social vulnerabilities. And then, of course, back to the IRMA map, we see specific places, and you can see many places when we start diving in where we have high social vulnerability and high impacts from IRMA in Miami, many more in the central part of the state. But again, understanding these social vulnerabilities and overlaying them with outcomes helps us gain a better picture of where we're standing. So how are products consumed and what are the constraints? I would say users, and that's academic and practitioners at large, do not have the capacity, the time, or the talent to dive deeply into data. This results in communities, whether they're researchers or practitioners, relying on data that's freely available and simple to map or bring into Excel. Most people only want to know, is it high, medium, or low? Many people don't get into the intricacies of how vulnerability is manifesting itself. I would argue for folks that are working in coastal areas with NSF funding like CoPe, that you'd want to understand that more nuanced approach to social vulnerability and not just is it high, medium, or low. So what's happening is a lot of folks are using this and making decisions based on this final score, this final number, this final color, without understanding how the data was derived and what it really means, leading to several challenges, including a lack of understanding about those interconnections or the complexities, a lack of understanding about how the shocks, stresses, connected disturbances, and linked events connect with social vulnerability. And so perhaps many decisions that are being made with an incomplete understanding of what's happening, and they might be missing the mark. So what data are available? Well, the US Census provides data, raw data on indicators. That's easy enough, but I would argue without the nuanced understanding of the concepts behind social vulnerability that you can't just go grab census variables, put them together and say we're representing vulnerable constituencies. They provide data, though, down to the block group for every year since 2010. The CDC provides tract level social vulnerability data. 2000, 2010, 14, 16, 18. I say this, the CDC's social vulnerability index is not the same as SoVI. Many people don't know this. So you have the CDC SVI, and then you have the social vulnerability index SoVI. Social Vulnerability Index provides annual track data for the whole United States, 2010 to 2018, for every state, county, city, congressional district, watershed, and/or user-defined area coming, which will be coming out later this month. So how different can they really be? Just as a representation, here's SoVI on the left and the CDC's SVI on the right, with the same data from 2014 for the same place in South Carolina. And so you can see how these indexes produce significantly different results when it comes to understanding spatially where vulnerability is. I say this only as a caution and to have your scientific brains think about this as you process through using these different things. I'm hearing that I'm almost done. I think this is my last slide. All vulnerability models are not created equally. The social vulnerability, the main differences here, you can see these on the vulnerabilitymap.org site, is the difference between an inductive, deductive, and hierarchical approach. You know, so just in how we create models makes them different. And the takeaways: understanding vulnerabilities is paramount in developing solutions. All vulnerability measures are not equal. Please make sure when you're employing vulnerability measures that you do so with a detailed understanding. I would even argue so far as to include those vulnerability scientists. This way you can build those appropriate solutions. And with that, I leave you with my contact information and open it up for any questions.
Hey, thank you, Chris. I appreciate that. I think we probably don't have much time for any questions yet, but maybe at the end of the morning, there is a Q&A session. So if you have a question for Chris, and I hope, Chris, you can stay around for that, we'll ask some questions at that time. I also decided to, since Todd has no power, he's in Utah, we'll bring him at the end of this session. So let's go to Sam Brody, Center for Texas Beaches and Shores. He's going to talk to us about Texas Disaster Information System. So Sam, can you share your screen?
I am trying to share my screen and I'm getting a...
I'm trying to stop sharing, so.
Yeah, maybe when Chris stops sharing, you can.
Don't know how to stop sharing.
Maria, can you help?
Yeah, I think I already make him a presenter. I'm Brody.
It says open system preferences. GoToMeeting needs to use accessibility features.
That's weird.
So when you click the icon screen, it shows that it appears that accessibility.
Yeah. Huh. And then when I click on it, it doesn't do anything.
Okay. You're using multiple screens, maybe? Accessible, yeah.
In the interest of time, I can just talk.
No, you can try one more time. Can you? What does it say when you click on the accessibility feature?
It says GoToMeeting needs to use accessibility features.
And do you know what they are?
Restart GoToMeeting and apply your changes. Open system preferences, but then nothing happens. Let's see this.
Yeah, it might be like a security issue that you have to give access to GoToMeeting.
Huh. It's never happened before. Turn off your audio.
Oh.
You can send us your presentation and we can share it from our screen.
Okay. Who do I send it to?
You can send it to me, you can send it to Ove.
The email?
Yeah.
Can you tell me your email?
Maria, can you give him your email?
So it's MPULIDO, Pulido.
Okay, I got it.
At FIU.edu.
Sorry, everyone. I've given so many presentations recently, and that's never happened.
Yeah, you know, This
Great.
GoToMeeting is probably new to your system.
Yeah, but I've used it before.
Really?
Maybe it's a,
You're using a Mac or Windows platform?
it's a Mac.
Okay.
I know.
No, it's okay. I mean, maybe others who have Macs could probably chime in.
But I've used this, and I have actually have it installed, the app installed on my computer. But the email should be in your email box.
No.
Still haven't received anything. So I'm just gonna give a few minutes.
Might be good for you to sign out and sign back in to see if that helps.
Yeah,
Other
I can do
things I've
that.
seen. Yeah. If you want,
All right,
I can go to the
go
next talk. You know, we can swap these things around if you like. Or you want to
Sure.
try to
I don't want to hold up the conference. So
No, it's okay. I mean, we kind of expect these. You think you can sign back in and that?
yeah,
Okay.
let me try to even come back.
Yeah.
Oh, I just got his presentation.
Say it again.
I just got his presentation.
Can you start it and start sharing just in case? So when Sam comes in, you can move the slides as when he asks for it.
Mhm.
I still get the same. Oh, hang on a sec.
So
I mean, I just got your presentation, so I will share for you.
Okay.
Is this your screen we are looking at?
Yep.
Okay, go ahead and share it then, I think. Or make it full
No.
screen and let's go.
Yeah, I think I'm the one sharing it, if I'm not wrong.
Okay,
Yep.
Can you make it full screen, Maria? And then Sam could ask us to move the slides.
Great.
Is that okay, Sam? Yeah.
That's perfect. Thank you, and I apologize for the
No
technical
problem.
delay.
No worries.
I'm going to provide a practical example of taking our data, models, innovations from the university and academic sector and converting them into a format that informs decision makers, policy makers, with the goal of making better decisions in the face of rising disasters in Texas, and that is what's being called TDIS, the Texas Disaster Information System. And I'm going to tell it like a story. The seeds of this started in 2017. Next slide, with Hurricane Harvey, which was and still is the biggest urban flood event in U.S. history. And this storm was so big and so damaging, it's going to be generations to recover, that the state responded in a very different way. And that is, among other things, the state turned to the university, Texas A&M, and other universities to better understand from the knowledge innovators and the researchers and the practitioners in the university setting how to respond and set up a system and a set of policies that will presumably make Texas more, in this case, flood resilient into the future. Next slide. And so my team was asked to do all the data analytics behind this report called Eye of the Storm, which you can get online all over the place, and write the mitigation and recovery sections and policy recommendations for the report. And this was a really unique opportunity because we were directly injected into a community of the top level decision makers for the state in what to me seemed like an informal way to try to get a whole handle on what happened, why it happened, and what to do about it. And one of the first things we did was, when I was asked to write this report, I was adamant that there had to be a data legacy established that was accessible to everybody. And at this level, people really didn't understand what that meant. And I was making more work for myself, but I wanted to create these web dashboards, data dashboards, so that it wasn't just the head of the Texas emergency management that could get this data, but anybody. And it's the same data that went into the report that provided all the descriptive analytics and the maps. So we did a series of what we call dashboards, and this is one of them, next slide, where in a couple of weeks, we're able to take all this data that we're collecting and convert it into a web interface where anybody could access everything from structural damage to insurance penetration, next slide, to hazard risk zones, to socioeconomic information, and combine it and graph it. And this, we were able to leverage decades of doing this for other projects and across the state. So we're able to do it really quickly. And the major comment that came out of this was, hey, why are we not doing this all the time? It was very helpful. I remember the head of emergency management, he just wanted to know how many flood insurance policies were in this county on the coast. I was like, you don't know that? That should be at your fingertips. He's like, I just want to know how many insurance policies there are. That would be a game changer for me. And here we've been measuring, mapping, modeling insurance issues for the last 10 years. This was very easy for us to do, and we did that. And that sparked this ongoing discussion that was germinated from the very top. We should be doing this all the time, and translated into, well, why don't we have an information system, next slide, that is collects, stores, reconciles data, provides decision makers with this data in a way that is usable, interpretable, and action oriented, be able to share that data across different agencies, which I've learned is a major challenge, and help Texas make better decisions by combining social, physical, environmental data and the models in a concerted way. Next slide. So this discussion has now been going on for 3 years, and we've had an opportunity to crystallize it, understand it. Now we're planning for it, and then we're going to build it and deploy it. And this is a 12-year, $50 million project, which sounds like a lot, but it's probably half of what we need to do what's being called for. So this is a long-term play, and it's been a real challenge to merge the researchers and the modelers with the action-oriented decision makers over a decade-plus period project where people's attention span is often 30 seconds, at least mine is. But there are 3 major components to this system. One is, and I put this out as the challenges we're realizing in this project for others to learn from all of my pain and all of the mistakes and the victories we've had along the way. And this is at the very beginning of this project. And those 3 areas are collaboration. Collaboration is the first thing. Data sharing agreements. You would be surprised, or maybe not, how difficult it is to have agencies, federal and state and local, share their information and do so in a way that is secure and adheres to all the bureaucratic and administrative protocols. Next. The second major part of this is building the architecture, acquiring the hardware, or leveraging existing hardware, and archiving it, reconciling it, and figuring out how to deliver it in a way that's useful to different audiences. for the same storm from different perspectives. And that's a real challenge, and there's no way to satisfy everyone. But we've got 12, maybe 20 years to do it. So again, it's a long-term play next. And then finally, and this is my area of expertise, developing the tools and applications and visualizations that can inspire leaders, decision makers, and even individual residents to mitigate and take action. This is supposed to be for all hazards. We're going to start with floods, which is my expertise, and then move to fires. And then maybe I've retired and someone else picks up drought or something. Next. So the way we envision this system is a systems within systems, and that's both from an architectural standpoint, data architecture standpoint. There'll be multiple APIs within APIs creating pipelines, and we're going to work with a lot of different people on that. But essentially, it starts with stakeholders that inject the data. The data and the models are constantly being circulated, improved, and then the output goes back to the stakeholders. So it's almost like a spinning analytical top on the web with visualizations, tools, and products that spits off those tools and products to the stakeholders, which right now are decision makers primarily, but all stakeholders, to make better decisions. Next. We broke up our project into 6 different work streams, and it goes from data strategy, which is where we are, and stakeholder coordination, where we are now, all the way through creating a human-centered product or system that is constantly being updated, evaluated as data and situations change. I am very scared of real time, and so I've been pushed along the way, and now it's near real time. But to me, this system is more about mitigation and long-term recovery than it is real-time analysis, although others would disagree and want a more real-time interface. Next. Let's skip that. Next. So at the end of the day, for me, as a statistical researcher, I do observational statistical models. It's about taking, in this case, these are 1 million points of impact of damage during Hurricane Harvey over a 43,000 square mile area. How do you take this confusion of points and data streams next that comes from, in this case, FEMA, and put it into a format that someone can click on? In this case, looks like a block group and census block group, and get information both historically, during an event, and then thinking about scenarios, long-term planning. Next. So I'm going to leave you with lessons learned. So this is probably the most important slide I have. And again, it's what have I learned that I can share with you as the audience? And that is a couple things. First, building this system is more about human values and their relationships than anything else, which is something I think is really important. And it's not just, as Dr. Emmerich described, it's understanding the spatial distribution of those characteristics, but it's also understanding that this is everything is subjective, and how we collect, store, and articulate data is really about human values. The second major lessons learned is we established a steering committee of all the state agencies, federal agencies involved, and leading academics and modelers, one of which is in your session, Ali Favi today, who is a great colleague and is a part of this. That really is helping build participation, a sense of ownership, so that this is not coming from some either top-down directive or group of academics that got some grant. This is coming from the mainline agencies themselves and the people who really need the information to make these decisions. We hired not just a bunch of data architects and database managers and computer experts, but we hired a communicator. And that's as important as anything else that any other person we hire. And that communicator is the interface between the steering committee and the project personnel, so that it can't just be me as a professor. It's got to be a professional who's constantly communicating, getting input, and baking that into the product the best we can. We are partnering with what I call legacy organizations. So we just sealed a formal partnership with the Texas Advanced Computing Center, which is where 80% of all the high performance research goes through in the United States. And it's like adding, adrenaline to an already really energetic team. But it also leverages teams of other people, in this case, buildings of other people, and brings to the forefront this knowledge that is going to last and personnel way beyond the initial team. So partnering with not just an individual who's hired and will leave and take that knowledge and history, but organizations and people within them where that knowledge and that momentum can remain in place, particularly since this is a decade-plus long project. Human-centered design and implementation is so important, and having the time to go out and meet and have workshops and understand how people perceive and act upon data, and it's really hard to do in academics because we tend not to have the time, is really important. And then finally, building a system that is, they call it agile, I call it adaptive. As the data changes, the landscape changes, the problems change, the hazards and disasters change, it's really important from day one to design a system that can accommodate. And in general, this is about bridging the gap between, again, the researchers, the modelers, the data scientists, and the decision makers and the residents that live in Texas. And I think it's a really good model for others to use, where finally, the state level decision makers are turning towards the universities and the knowledge creators and trying to come up with systems that bridge that gap. And this is what the Texas Disaster Information System is all about. So thank you very much for inviting me today. And again, apologies for the slow start. I'm really grateful to be part of this and be part of so many great speakers today. Thank you.
Great. Thank you, Sam. Really appreciate great lessons there. I hope we can continue this discussion and interaction. In the interest of time, let's move on to the next talk. We can come back to the time when we have Q&A. So the next speaker is Jonathan Gilligan, and he's from Vanderbilt University. He's going to talk about accounting for human behavior in models of coupled natural and human systems. So Jonathan, can you share your screen and start? Okay, can we hear you, Jonathan, or I cannot hear you.
You're muted, Jonathan.
Sorry about that. You should be able to see my screen now.
Yeah.
And very good. So I'm going to talk today about incorporating human behavior into models of coupled natural and human systems. And in the spirit of this workshop, I'm going to talk a lot about the challenges rather than the great successes here. And so I'm going to highlight this and focus this on from a paper I was part of that came out earlier this year that identified 8 grand challenges for making coupled socio-environmental systems models useful to decision makers. And with this short talk, I'm going to focus on 2 of these challenges. Combining quantitative and qualitative data and methods is a big challenge and opportunity, and integrating the human dimension into the models is very important. So behavioral science perspectives are really important. Most models that are used to inform policy on environmental issues represent human behavior in simplistic economic terms such as rational utility maximization. But behavioral science tells us that real people behave differently. They follow irrational heuristics and biases. Emotions play a very important role in how people perceive and respond to risk and uncertainty. And then interactions among people add complexity. So individual decisions are not just based on maximizing the material benefit to the individual, but are strongly shaped by the perception of social norms, how other people are going to, what kind of behavior other people expect, what they see as acceptable and unacceptable behavior. So I'm illustrating here on the right how the, this is from about a paper by Brian Beckage and others that was one of the first integrated assessment models of climate and the economy to incorporate psychologically realistic behavior. And so in this, human activities producing greenhouse gases, which produces climate change, which leads to extreme weather events. And then those shape the individual's perceived risk from climate change, their direct experience of those or reading about them in the news. And that perceived risk then interacts with the external social norms that the person feels. What kind of behavior is expected of them? What do their peers, friends, family think are acceptable and unacceptable behavior? That interacts internally with their perceived self-efficacy. Do they believe that their actions can actually help to reduce the risk that they're facing? And if so, those 3 things, the external perception of risk, the social norms, and the internal perceived self-efficacy, then shape their decisions about energy consumption, which then over the course of years and decades feeds back to shape the exposure to extreme events. And this illustrates how the internal psychology, the decision-making, really matters when we want to understand the human part of a coupled human and natural system. And so for studying these kinds of things, agent-based models can be very important because they build up the societal level phenomena from individual level decisions and actions. And they have the potential for heterogeneous population in which not everybody thinks and acts alike. And the interactions between individuals, the individual decision processes are built right in. But there are challenges in building these models because we have to think how to structure them. We need to know how individuals make decisions, how individuals interact with each other, and how they interact with the environment. We need to think about how we calibrate and test these models. And so in the use of data here, I want to argue that qualitative data is very important. Quantitative data is wonderful, it's really useful. But an agent-based model, in fact, a lot of simulation models are in effect narratives. They tell the story of how our theory of human behavior plays out in a context of a coupled human and natural system. And qualitative data, such as ethnographic data, data from key informant interviews, can be really valuable in shaping and informing that model structure. And in evaluating the performance of a model, quantitative predictions are really great. But there's growing attention in the modeling community through pattern-oriented modeling and things like that towards the role of qualitative model evaluation. Does the model qualitatively reproduce the kinds of big patterns that we see in the system that we're studying? And so an example of the key role of decision-making, this is from some work I did with my graduate student, Emily Birchfield, a few years back, studying how rice farmers in Sri Lanka make decisions when they're facing drought and water scarcity. And I'm not going to go into the details, but this is based on both historical data about crop yields, field work studying how farmers were behaving during a big drought in the summer of 2014, and we built an agent-based model to study how the growing prevalence of private dug agricultural irrigation wells was affecting the community's response to water scarcity. Normally, rice farmers use shared reservoirs and distribute irrigation water through canals. When they have a private irrigation well, how does that change things? And we're looking at a specific case of how the farmers switch from growing rice to growing vegetables. Growing rice is more of a collective activity. Growing vegetables is more of an individual activity. And this, the top row of these small multiples shows conditions when there's lots of water in the reservoir. If the monsoon rains don't come, they're still not in trouble. The bottom, the reservoir is low. If the monsoon rains are bad, they don't have anything to fall back on. So it's a higher drought risk. And then the different columns are different psychological models of decision making. And on the right, different farmers have different models. And without going into too much detail, each small multiple is looking at how the x-axis is the fraction of farmers with a private well, the y-axis is how many switch from rice to vegetables. Under high-risk conditions, all of them pretty much switch to vegetables when there's more agricultural wells. But when we look at the low-risk situation, there's a really big obvious difference between prospect theory and the other two models of decision making. That indicates that we really need to understand decision processes. So some other students on our team followed up from this work by going out and doing some experiments with interactive games with farmers to understand their decision processes better, because we identified that was really important for the project. Another place that I'm working on this is environmental change and migration in coastal Bangladesh, a very tightly coupled human-natural system where land use affects natural hazards. Here, this earthen embankment in the picture at the top is part of a big system of embankments built for flood control in the 60s and 70s. And these block seasonal flooding from the monsoons. They block tidal flooding in the tidal channels near the coast of Bangladesh, but they also block sediment from coming onto the land. And that leads to accelerated subsidence behind the embankment. In this site, it's not visible in this photograph, but on the other side of this river, there's a natural mangrove forest. And my colleagues have been studying the sediment transport there and found that from year to year, the tidal flooding of that forest platform brings enough sediment to keep the surface of the land in homeostasis with sea level. So as sea level has risen, relative sea level for the forest has not, because the land rises from aggradation just as fast as the sea level does. But inside the embankment, that accelerated subsidence and the lack of new sediment has led the land inside the embankment to be about 1.5 meters below where the forest on the other side of the river is. And that led to catastrophic flooding in 2009 when a cyclone breached the embankment and over 40,000 households were displaced. Their homes were underwater by 1 meter or more for about 1.5 years before they could fully repair the embankments. So we have growing hazards caused indirectly by the land use, and then that environmental stress from those hazards then affects society and brings us into the closed loop of the coupled natural and human system. This project is looking at how all of this interacts with population migration. And there's a simplistic picture that as sea level rise happens, or there's drought or flood, some disaster, and then there's just some huge mass out migration of refugees that strains the political systems in nearby countries. But migration is much more complex. There are active migration patterns throughout South Asia for more than 1,000 years, and they follow economic opportunities and social and cultural connections. And then when environmental stresses come, those interact with the existing patterns. So the historian Sunil Amrit, writing about environmental influences on migration in the 18th and 19th centuries, writes that what appears to be natural takes work. These migrants are not just reacting blindly, but the environmental stress interacts with the bigger migration patterns. And here we see on the right how farmers from an area I was studying who weren't able to grow rice in their homes because of recent flooding had traveled about 100 kilometers to work on other farms, and now they're coming back at the end of the growing season. They took their wages in rice, and each of these farmers is bringing back a few hundred kilos of rice that can then feed their family for the rest of the year. And this illustrates how migration can be both a sign of system failure when people get desperate and leave, but also resilience, where seasonal or temporary migration and remittances that are sent home can actually strengthen the home community during a period of stress. So to gather data on environmental migration or on migration and environmental change, I'm part of an NSF CNH project in which my social science colleagues, Catherine Donato and Amanda Carrico, are leading the Bangladesh Environment and Migration Survey, which is a retrospective household survey that captures the lifetime migration history for all members of a household. Phase one of that, which we did a few years ago, captured almost 1,700 households in 9 communities, illustrated by the green dots in the map on the right. For each of those households, it captured almost 2,000 variables representing the migration history of 3,000 individuals. Phase 2, which they just completed last year, captures 4,000 households in 20 communities. And then this leads us to the question of how to assimilate and deal with all of this data. When we want to integrate this data into our project, we're combining the migration data with data on weather, changes in land and water, and then how do we do the analysis? Sometimes we have a theory-driven hypothesis, such as we think extreme weather affects marriage rates, and then we can do conventional regression or survival analysis, such as shown on the right here, where we see the longer the duration of an extreme heat wave, the more likely young women are to enter into marriage. And we find, moreover, that those marriages tend to be very stressful. The marriage partner, the husband, tends to have lower income, less education, and to be more prone towards domestic violence. So these women become more at risk in this, and this is one measure of the kind of stress that's produced by the extreme weather. But other times we don't have that kind of hypothesis-driven analysis, and then we've got thousands of variables and we have to make sense of them. So we're applying machine learning models, and they show promise at identifying salient variables. Particularly, random forest models seem to be promising, but so far our predictive skill from the machine learning is disappointing, so we're continuing to work on that. And as always, qualitative data, ethnographic data, data from interviews is really important in developing and guiding theory and hypothesis. So this is my last slide. We don't have great models to talk about right now. We're in the process of developing models that are drawing from this empirical data. And from the literature, we see that the political economy is a very important linkage between environmental stress and outcomes such as migration and marriage, and community and social networks are important. A real inspiration to us has been some work by Clark Gray and Valerie Mueller from 2012, where they found that if a disaster affects a small fraction of a community, migration tends to drop because it costs money to migrate. The environmental stress leads people to look for wage labor jobs within the community. But if the disaster affects a large fraction of the community, then out-migration can tend to rise because there are more people looking for work than there are local jobs. And so our model development is focusing on the local political economy and looking at how migration can then indicate either a system failure, indicating desperation, or can be a source of resilience and adaptation to environmental stress. So this is work from a deep interdisciplinary collaboration, and we're very grateful to the funding that supported it, the students who worked with me, and all of the terrific collaborators in many disciplines who have contributed to this. So thank you very much for listening.
Hey, thank you, Gilligan. Great presentation. Didn't realize you worked in the place where I am from, Sri Lanka. But,
oh, yes.
Yeah, interesting. if you can stick around towards the end of this, end of next session, we have 15-minute Q&A, so there might be some questions from
I
the
will be there
audience.
for the Q&A.
Okay, thank you very much. Let's move on to the last talk in this session, and then we'll get into Todd's presentation, which was supposed to be at the beginning. So the next talk is by Ali Mustafawi, Texas A&M University, and he's going to talk about the complex modeling for robust application planning of infrastructure systems to sea level rise impacts. So Ali, can you share your screen? Ali? Uh-oh. Ali, can you hear me?
It's frozen.
Or is it frozen? You're muted, Ali, I think. That's one
He's
problem.
going to sign in again, probably.
Yeah.
What a day we've been having, huh?
I
Challenging.
know. Yeah. Well, that's technology. But Todd is back. Hi, Todd.
Hey guys,
Yeah.
I'm sitting in an ATM in a bank with a generator.
Oh, my
great.
goodness.
So
Maybe we should
we-
let you go
Maybe I
first.
should go.
Yeah.
Maybe I should go.
Yeah.
What do you think?
Okay. So
Yeah.
we'll,
Okay.
Ali, I will let Todd go first, and then we'll come back to you, Ali. Is that okay with? If that's okay with you? Ali, so let's go with Todd. Todd Kroll, Director of the Institute of Environment at Florida International University. I asked him to talk, actually give a welcome and talk about vision for observation models in physical, social, and economic systems in Coastline. So, Todd,
Are you seeing my screen?
we can you make it full screen? Okay,
we go.
good. That works great.
Okay.
Thank you.
Okay. I'm so sorry, everybody. Of course, technology. We're having a huge storm. I'm in Salt Lake City, 50-mile-an-hour winds. There are trees everywhere. So I'm sitting in an ATM machine where they have a generator going. I'll try to go a little faster. First of all, I'd like to thank and congratulate Obey, Sparkle, Mike, and Tiffany. Thanks for putting all this together. But as best as I can tell, you guys received one of the very first CoPe awards from all of NSF. You were in the first cohort of people who had successful proposals. So congrats. So just to put this in the setting, of course, coastlines, especially urban coastal areas, are going to become increasingly important, increasingly populated. The data are pretty clear that more and more people are moving to coastal cities. I just want to bring your attention, if nobody else has, I'm sorry, I was listening on the phone. If you haven't seen this synthesis report, you should see it. This is what NSF's vision of what CoPe looks like, a report put out in March by Tutanico et al. That basically talks about the importance of inclusive diversity, social equity and justice, basically a bottom-up approach to understanding coastlines, what the people want, what the people need, what people think about. And then, of course, there's environmental change, and I'll spend some time talking about that. And then finally, the data have to be accessible. One of the things that I think NEON was an interesting first approach at a platform for cutting-edge science questions, but the data aren't necessarily readily available to most people, and I think NSF is cognizant of that. So we have to think about how we serve data in a way that is useful to the community. So this is sort of the convergent science that NSF envisions. So we have local issues, we've got inclusive diversity, and then we've got, as Obey started with, this sort of intersection between biophysical, socioeconomic, and even political processes. And so again, co-production of questions, data access, and interoperability, okay? So this is how we're thinking about it, and by we have a whole group of collaborators, including Obey, Tiffany, Mike, a whole variety of folks across South Florida who are thinking about trying to pose questions in the framework of hazardscapes. So dynamic systems, which reflect the physical susceptibility of place and vulnerability of human life. And so here we've got these biophysical stressors and shocks, socioeconomic, socio-political, and then all these things interact together to create sort of a socio-political response that really needs to be driven by the community. It's important in Miami, especially, that we put in that political part because Miami is such a political place and so many decisions occur from a top-down perspective. So that's one of the barriers, I think, that are particularly difficult that we have to make sure we break through. I want to use a very recent event to try to use this hazardscapes construct to think through what a coastal observatory might look like. So about exactly a month ago, on August 10th, we had a huge fish kill in northern Biscayne Bay, which is the bay that's right against the city of Miami. We had all kinds of a big algal bloom followed by an oxygen sag at night, not surprising, and then a pretty major fish kill. And this is, I hope you can see this movie, but this is what the whole bay looked like for a couple of days. I mean, I have never seen anything quite like it. We've heard about these kinds of algal blooms on the eastern coast in South America, but this is the first time I'd ever seen something sort of this significant. And so it's not too surprising that almost the entire north half of Biscayne Bay went anoxic during this event. So let's go back to our hazardscapes. What should we have known to predict an event like that, and how could we have known it? And so let's go through this process of building a multimodal coastal observatory using this sort of construct to see how we would go about not only understanding what happened, but more importantly, predicting what is likely to happen. And then most important is how to engage the local communities and understand what they think happened, what they care about, and where they want to put the emphasis on sort of making our coastal livelihoods resilient. So the first thing is, had we have been watching satellite images and how the offshore currents were working and sea surface temperature, what we would have known is that the water temperature coming off the ocean in July and August was about 7 degrees higher than normal. So we had a very warm current of water coming up from the southeast and coming right into Biscayne Bay in South Florida. So that's the first thing we should have known, that with that warm surface water was coming off the coast to the bay. The other thing we could have known and should have known from our tide gauges is that at particular time, late July and early August, had particularly low tides, particularly low currents, and so very low circulation potential. And you couple that with Biscayne Bay being heavily modified by humans with multiple causeways, multiple bridges and roads, which are blocking sort of circulation from north to south. It should be not surprising that we had sort of a warm standing body of water in Biscayne Bay that typically sort of mixes fairly normally. The other thing we should have known, and we do know from the airport climate station, is that July precipitation averages about 5.8 inches. This year we received 10.3 inches in July, but most importantly, most of that rain came in 3 big rain events, which meant localized flooding, groundwater saturation, and the interaction of surface water and groundwater sort of pushing towards the coast. Sorry, somebody came in to use the ATM. So July precipitation was higher, 3 big storms. So Biscayne Bay is fed by 6 major river canal systems that drain the greater Miami area. So from the Everglades all the way down into the coast. And what I've highlighted in the black box here is the little river system, and those red dots are from the Department of Environmental Protection that show that there was huge amounts of total phosphorus in a couple of their monthly study sites during this sampling period. So what we should be doing is having things like this buoy system that are continuously measuring temperature, dissolved oxygen, chlorophyll, nitrogen, phosphorus in all of our canal and river systems that feed into Biscayne Bay. And in fact, we have those, and Tiffany Troxler and her lab and students have been running one of these in the Coral Gables Canal system for almost 2 years now. But these are expensive, they're hard to keep up, and you need a lot of them. I said there are 6 canal river systems coming into the bay, so it's quite an investment. And as most of you know, if you're astute at water chemistry, measuring nitrogen and phosphorus with sensors in salt water is not a trivial thing. And so there's still a lot of sensor development that has to take place for us to be able to actually watch the important pollutants in these canals and saline bay systems. The other thing is we could employ these same kinds of buoys to understand what's happening on a continuous 24-hour basis. A lot of the environmental protection agencies, a lot of the management agencies take these once a month, once a week static measurements. They're almost always taken during the day, but as we all know, oxygen sags always happen at night when the algae are sucking up the oxygen. And so we do have these deployed in the bay, and we did in fact watch the oxygen go to 0 in 2 of our places within the bay. But again, a buoy only measures within about a meter of where you place it. So to understand an entire coastline around the greater Miami area would require more than just these kinds of point-by-point buoys. So we need to start thinking about deploying all the possible autonomous vehicles that we now have at our disposal. Again, nitrogen and phosphorus sensors remain an issue. We're working on that. But we should be using these autonomous vehicles as a sentinel system of coastal sensors to help us understand what's happening at sort of more continuous spatial scales. And in fact, during this thing, we did develop the autonomous vehicles we have. On the left, you see all the different you can see all of the different points that were taken. Blue represents oxygen above 4, and red less than 2. Of course, anytime you have oxygen less than 2 milligrams per liter, fish become physiologically stressed and mortality exists. On the right-hand side, you can see 2 of those systems that I told you about that feed into the bay. The lower one is the Little River, one anoxic point way up, but then the Biscayne Canal at the top, you can see all those red dots. So there was a whole bunch of anoxic water, and look, it's right against a golf course. Surprise, surprise, we had a big flooding event running off a golf course that probably put on a fair amount of fertilizer and insecticide, and that whole upper canal system basically was anoxic. So that's the biophysical stuff that we should have known. But as I heard a couple of the speakers discuss already, and the intention of CoPe is to talk about what about the social fabric? What about those socioeconomic, socio-geopolitical issues that underlie everything we do? And so to really understand this phenomena, to really try to grasp what the communities think and how to make real change so that we don't have these fish kills and anoxia events in the future, we really have to understand what the population thinks, what they understand, and quite frankly, what they care about. And if you look at the figure at the lower right-hand side, and I thank Obey's postdoc Jagath, who put all these land demographic information together for us in a pretty short period. Those colors are households that are less than $50,000 along the Miami River, which is the major tributary of the northern part of Biscayne Bay. $50,000 in Miami doesn't go a whole long way. The darker the color, the higher the proportion of households in that drainage that have houses less than $50,000. And so what you see is a pattern that's not too surprising, right? You have fairly wealthy people living right out on the coast. They have the $1 million mansions, they have the big condos that are overlooking the bay, and they, of course, want to enter their front yards, depending on the case. And then as you move farther inland towards the airport at Miami International Airport, you get more and more small neighborhoods like Little Haiti, Little Havana, a variety of small sort of culturally diverse neighborhoods in which you get less and less disposable income. The other thing that you find out when you start digging into this kind of demographics data and historic, cultural, ethnic diversity information is not surprisingly probably to many of you, is a lot of those lower income communities also have pretty old and fairly basic sewer systems. In other words, a lot of those households are on septic. So there's no central pipe system. When you have a flood event where you get groundwater saturation,
Todd, if you can hear me, I want to recommend you terminate your video. Your
flood
connection
all
is
the
spotty.
fields in a neighborhood, and you flood septic fields in a neighborhood, it should not be so surprising to us that huge amounts of nitrogen and phosphorus. This idea, the demographics that underlie the area we care about are vitally important as well. So then here's what we end up with using our hazardscapes approach. We have stressors, which are those long-term press disturbances. We used to call these presses and pulses. But stress is things like increasing temperature, changing tidal currents, and precipitation changes. Those are directional changes that are going to be with us for hundreds of years. Then we have shocks. We had that high rainfall. We had groundwater saturation. We had those things that basically led us to the responses of flooding, nutrient transport, ultimately algal blooms, and fisheries collapse. We also had the socioeconomic stressors of increasing bay development, changing land use, and aging infrastructure, right? As time goes on, the infrastructure gets older. And then we have economic disparity that even, and especially now, continues to be exacerbated. And then the shock was expanded built environments all around the area. You could see all kinds of sediment plumes coming into the bay during those high rainfall events because we continue to build high rises and replace buildings right along the Miami River, right along the bay. And then ultimately we have a failing of infrastructure. And then the socio-political part, the South Florida Water Management District, which manages many of these canal systems, has the mandate of protecting life and property. It's all about not allowing local flooding events and people to be flooded. There's no water quality criteria by which they operate the canals that they have. So when a big storm is coming, or when there are high rainfall events, they open the gates and let the water flush from inland out to the coast. And they do that to basically minimize flooding. There's no way for them to prioritize which canals or river systems they would let flush based on water quality criteria. So that's a socio-political change that we would have to affect to actually make management decisions based not just on the amount of water and flooding, but also on the water quality that we would end up delivering to the coastal areas. And then, of course, elections matter. It depends on who the mayor is. Our current mayor is interested in the south part of the bay. He could care less about the north part of the bay. As long as the south bay looks fine and is operating fine, then he says the bay is fine, and he's not really willing to think too much beyond that. So OB asked me to say, what kind of modeling would we need? Well, in the end, to understand exactly what happened, that middle thing, the intra-bay circulation model, we would have to understand. But that would be a joining of a large-scale circulation model from the deep ocean in, and then a coastal surface and groundwater flow model from the near shore inland. But more importantly, we need to mix those with tributary water quality models as well as surface and groundwater water quality models. So those things all have to get joined together if we're actually going to fix, not just predict when and where we're going to have issues, but try to do to take some intervention to create some socio-political change that would minimize these kinds of events. And what we really need is a really high-level coastal surface and groundwater flow model that includes nutrient transport so that we can help the communities identify those areas that have particularly failing sewer systems, bad stormwater drainage systems, and high densities of septic systems so that maybe we can use those systems with newer, better infrastructure to minimize the amount of nutrients that are leaking and moving into the bay. This is from a colleague of ours from Florida Atlantic University. He runs an institute for embedded from Florida smart sensor networks. And he says, here's the real challenge. The informatics system that you would have to build to take all of these continuous real-time data plus satellite spatial imagery, plus the monthly or weekly site samples by all the management agencies, not to mention all of the socio-economic and political data that have to underlie all this, is going to take quite a monumental effort in just data storage, data merging, data acquisition, and ultimately serving the data in meaningful ways, vis-a-vis visualization and ways that local communities can use the information to make decisions at the household and community level. And then finally, this is from Obey. This is how it all has to come together, right? We have to merge the physical, social, and economic systems across all of these different inputs and outputs, and using, because of the complex landscape of the data sets, some kind of machine or deep learning to sort of extract the information that we get from all these multimodal sources of data, and then most importantly though, to make them available for people to actually support them and help them make smart decisions. And I hope that was not too long. And with that, I thank you. And I don't know if there's time for questions.
No, Todd, no, thank you. Appreciate the great talk on models and data and also monitoring. So can you stay? Well, I was thinking asking Ali to finish his talk and then take a break, but I was wondering if he can rejoin when we have the Q&A session towards the end of the morning, actually 11:25 or so. Will that work for you, or you have to go back home from the
Well,
ATM?
if the bank doesn't kick me out, I'm fine. I'll hang around. So.
Yeah. Maybe what we can do is have
right.
Ali give the talk, and then since you cannot be there very long, maybe we can ask any questions at that time. We have a 10-minute break after that. We can manage the time. Okay.
All right.
So thanks. Ali, can you share your screen?
Yes. Can you hear me?
Yeah, we can hear you. Go ahead.
Fantastic. And sorry for a hiccup earlier. I had some internet issues. So good morning, everybody. My name is Ali Mustafavi. I'm an associate professor with the Zachary Department of Civil Engineering at Texas A&M. Today I'll talk about complex modeling for robust adaptation in infrastructure systems. And I show the idea of complex modeling in the context of sea level rise. Before I start, I think the previous presentations actually were very relevant to what I'm going to present, and basically demonstrate the need for having coupled models, or what I call complex models, for decision making and data-driven planning. What I mean by complex modeling in the context of this presentation is integration of models that are being developed across different systems, primarily environmental systems, human systems, and infrastructure systems. So we have been making excellent progress across disciplines to have physical models, numerical models, mathematical models, simulation models, etc., for examining underlying processes and interactions across different systems. For example, we have made very good progress in environmental models in terms of precipitation models based on downscale climate data, sea level rise projections, flood models, storm surge models, etc. So at the same time, in the realm of human systems, as Jonathan talked about, we have made very good progress in terms of understanding, the underlying mathematical laws that govern human decision making, and there are various theoretical elements from prospect theory, from theory of bounded rationality, etc., that could be used to capture human decision making, both on the side of the decision makers and planners and policymakers, but also on the side of the general population, to see how populations respond and react to different coastal stressors. And then the third component, which is the part that I focus mostly On the infrastructure system side, we have made very good progress on modeling urban scale systems, from road networks to water systems to power grids and their interdependencies, cascading failures, etc. So one limitation that currently exists is that these models are developed and utilized in isolation, in the disciplinary boundaries. And what I propose and talk about in presentation today is complex modeling, where we can leverage the existing models and improve them so that they can talk to each other. While the idea of fully integrated models that all run in synchronous times and having APIs that communicate with each other is ideal, and it should be the vision for interdisciplinary communities to pursue. At this point, I think before we reach that, we need to have a standard language and taxonomy and architecture, so that the models across different disciplines can see the interface that they have with each other. And I'm going to talk about two studies that my group has done, in the context of South Florida, in which we try to demonstrate the implementation of these complex models. So essentially, the complex models start with different elements. We have to have models that tell us about the environmental stresses, climatic stresses, and account for all the changes, climatic changes, sea level rise projections, etc. And again, those are models that are developed in the realm of environmental system modeling. And as I mentioned, there has been great progress on those. And then we have models of multi-sector stakeholder decision making. There are game theoretic models. There are empirical agent-based models that could be adopted to model how different organizations and different actors across urban sectors react to these stressors and how they make decisions, and see the effect of those decisions on physical infrastructure or engineered infrastructure, so that we can assess the vulnerabilities and fragilities under different scenarios of hazards, and also under scenarios of adaptation and decision making, so that we can have models that can help us evaluate different scenarios and different possibilities. One important thing to consider in terms of the introduction to complex modeling of natural human infrastructure system is that the goal of these models is not a prediction per se in terms of the accuracy, but it provides some tools to evaluate the probabilities of possibilities. So these tools provide insights about what would happen under 2,000 different scenarios, and how we can take action that minimize the impact, social impact, economic impact, etc., across these 2,000 scenarios, and what I call robust decisions that would lead to favorable outcomes across most of the scenarios, but not all the scenarios, because it would be very expensive to optimize a solution that is optimal across all scenarios. Anyway, so this is kind of a conceptual representation of complex modeling. Again, the idea is not integrate everything under one umbrella of a fully integrated model, but understanding the interface between these models and developing architecture and taxonomy that these models could be integrated. The first study that I'm talking about to demonstrate this complex modeling is the study of the impact of sea level rise on the road network in city of Miami Beach. The work is already published and is presented in this paper. I just provide an overview of that, but folks who live in South Florida probably live this day by day. That I remember one day I was driving in South Beach and I saw water on the street, and this was a sunny day. It was one of the very first experiences I had with these king tide days and sunny day flooding. And then after I engaged with other colleague Mike and others, and with stakeholders down in South Florida, we understood that this is a significant problem. And then one question was, we are implementing different adaptation actions like installing pipelines, thinking about elevating the roads, etc. How we can evaluate the effectiveness or long-term return on investment on these decisions, adaptation decisions, and models. So we created an integrated model. We call it a sea level rise simulation model. I give you a very quick overview of what is in the model. We modeled different scenarios of precipitation and sea level rise. We didn't do it ourselves. We used existing models. There are existing models based on downscale climate data that simulate different intensities of precipitation and different return periods. And we just developed what we call them surrogate models of those complex models that we just model them based on a simple probability distribution like Poisson processes, and then with different intensities. So we get the outputs of the very complex downscale climate models and make very simple surrogate models that can simulate at a given year what's the probability of having certain amount of rainfall. Another component of the environmental processes model is actual sea level rise. We used the IPCC projections and looked at the these slow, moderate, fast, and sea level rise, and then the ranges that it could happen, and then again models of sea level rise in Southeast Florida, and evaluated which roads could get frequent no-sense flooding, and evaluated again using surrogate models a simple representation of what's the probability that across different times in a year a certain road section will experience no-sense flooding. That's the environmental system model part of this complex model. The other part is the human system model, decision-making processes. We evaluated the risk attitude and decision-making processes of the organizations involved in decision-making, and used the theory of bounded rationality and regret aversion theory to model human decision-making under risk. And then the infrastructure system part involves the road network of the city of Miami Beach. And then we developed this model that all these complexities and interactions between different systems are captured in a multi-agent model, in which each agent is one of the systems, like the environmental system and the human system and infrastructure system, and each agent have multiple sub-agents and attributes. And as I mentioned, the details are in the paper, but then none of those are needed for running the models, or the knowledge of those are needed for running the models for general audience and stakeholders. We have these user-friendly interface in which basically these future scenarios are at the fingertips of the analyzer. So we can determine different analysis periods. For example, at the time we were looking into from 2016 all the way to 2100, looking into different budgets, annual budgets for adaptation actions, and annual maintenance and reconstruction processes. We look into different projections of traffic based on the projection in the population growth, or even population migration, and looking at different scenarios of sea level rise. I'm running the animation of the model, and I don't know whether you could see this. So by running the model, as you can see, the interface, we can determine the actual sea level rise, and then the perception of the agency. And here are the major links that we visualize. On the left-hand side, we can see different years passing by, and when roads with tinges of reds are the roads that experience significant deterioration over time. So basically, heavy precipitation and the sea level rise will accelerate the deterioration of roads. And then we also model different implementation of different adaptation actions, like pump station installation at different locations, and see to what extent they could reduce this accelerated deterioration. And on the right hand side, we have a series of metrics such as maintenance costs, life cycle costs, etc., that we can see how they change over time. So using this model, we simulated more than 2,400 scenarios, and we evaluated, okay, what's the how much budget we need to minimize the life cycle costs and the impacts of sea level rise, and what would be that budget effectiveness, level of budget effectiveness under different scenarios. So here is only one example of our model outputs, in which we see different budget levels, and this is annual budget levels. If we spend, let's say, $50 million a year, we can see that we can almost reduce the life cycle cost to a great extent. But as you can see, with lower budget level, $5 million or so, which was the case at the time we analyzed, the long-term life cycle cost would be significant, and there is significant sensitivity to what scenario of sea level rise would happen. Of course, with a fast sea level rise, we will have significant life cycle costs. And similar to that, we did another analysis in terms of the savings that could be achieved, the return on investment. So the bottom line was that, regardless of the scenario of sea level rise, adaptation has a very significant return on investment. And of course, if we have like a more severe sea level rise, the return on investment would be significant. The other question was, okay, when we can implement these as, actions. So we also analyzed, different time intervals. Oh, sorry. It seems that we have an echo. Okay, apologies. We evaluated different adaptation actions at different years, and by interacting with folks in city of Miami Beach and the transportation folks, and also Florida Department of Transportation, we received very positive feedback about how these model can basically support their planning and decision making. Another quick application that I want to go over is the same type of analysis and modeling, but for the water supply system and water supply system exposed to saltwater intrusion. So we developed a model, similar philosophy, similar elements, and the work is presented in the paper that I listed here. Basically, in the environmental system modeling side of it, we capture two stressors. One is the chronic saltwater intrusion because of the difference between the hydraulic pressure of the sea level and the groundwater, and the other one is the storm-induced saltwater intrusion. And I learned this from Mike, the wash over saltwater intrusion that can happen during the storm surge. Again, we didn't develop these models ourselves. We used the existing models. And for example, this paper that I said here modeled different scenarios of saltwater intrusion under different scenarios of sea level rise. And based on this, we can see, cumulatively as we move forward every year, how much saltwater intrusion we will have in terms of the number of fits, if we don't make take any adaptation actions, etc. So again, we didn't use all those complex groundwater models, but we developed the surrogate model that models the probability of saltwater intrusion and the extent of which at different years, and based on the locations of the well fields, and then also what water treatment plants use what well field, and also how many customers they provide. We use model the infrastructure system, and again model the decision making processes using bounded rationality and regret aversion theory, and implemented in the context of Southeast Florida, South Miami-Dade County. And then we have 3, water well fields, 3 water treatment plants, 1 population area that these 3 treatment plants serve, and then, evaluated, based on the locations of the aquifers, and then the, projections of the, saltwater intrusion. We have modeled different scenarios of adaptation actions like deep well injection, salinity barriers, relocation of the wells, and building desalination facilities. And all of these was again integrated in one model that in the back and it integrates all these elements, but in the front end there is a very user-friendly input interface in which the analyzer can look into different scenarios, different budget level, different risk attitudes, etc., and simulate the same type of dashboard. We see different performance measures. Here we looked into the different measures such as the level of water supply. We created a resilience index for that and evaluated the utility of different adaptation actions under different scenarios. Again, there are several outputs that we evaluated. So we evaluated, planning approaches like proactive adaptive planning versus reactive, and then evaluated under each of those, under different capital funding levels, how much long-term resilience we can achieve, and again, the integration of these elements enable us to have all the complexities of environmental system processes and stressors, human decision making, and infrastructure system all in one model. Again, some of these are the surrogate models of the actual models, but it provides us with complex modeling that we can model all these variables of environmental processes and human decision making and infrastructure systems all at once, and model different scenarios and probabilities of possibilities. So the takeaway is that I think my message is these are examples, but this provides promising evidence that these integrative complex modeling can have significant potential for advancing our understanding and better adaptation and resilience planning. And again, we don't look at fully integrated models that the flood models and climate models can work together with infrastructure system models. That's ideal, and I think that should be the vision. But I think at the beginning step is how we can, infrastructure modelers how they can understand the interface of their models with environmental models, and environmental models understand the interface of their models with the human system models. And if we can develop taxonomies and model architectures that these interfaces are clear, and we can all develop models based by recognizing these interfaces, we have better opportunities for integrative modeling. So with that, I close my presentation, and apologies again for the earlier hiccup, and I would be happy to answer questions during the Q&A.
Yeah. Thank you, Ali. I appreciate it. Great talk on linking models, and sometimes we have to simplify some of the complex modeling systems. So in the interest of time, I'd like to see if I can get back to some of the time schedules. Unless there is a burning question for Todd, I would like to, right now we have a 10-minute break on the schedule, which is what we will probably do. Is there any burning question for Todd? Otherwise, we'll go into the break, and we'll have some more time, perhaps before lunch or right after lunch for Q&A. I'd like to see if I can get back to the other speakers on time for the next session. If not, why don't we, so it's about 10:50 now. We kind of chewed up our break time with all those technological challenges. So why don't we get back in about 5 to 10 minutes, take a bathroom break or get a cup of coffee, and we will have the economic observations and modeling session. Mike Sukop will be moderating that. Anything else, Mike or Tiffany or Sparkle, I miss, or Maria?
Thank you, Abhi. Great first session.
Yeah, I think in spite of the challenges, they were great talks. I really appreciate that. So anyway, so let's meet back before 11 if we can.
Okay, I think we will get started. Jeff, are you there?
Yeah, Jeff Atkins.
Okay, very good, thank you. So let me just introduce you briefly, and then we'll get started with your talk. So Jeff Atkins is an economist with NOAA, the Performance, Risk, and Social Science Office in the Office of the Chief Financial Officer at NOAA. So he will be speaking about defining and measuring the U.S. Ocean economy. Thanks so much for joining us today. And we'll look for your screen. Let's see here. Yeah, okay, good. And the slide view would be good. Perfect. You're muted though. See, I think we might be able to unmute you from here. I can send an unmute request.
Okay, how about now?
Yes, very good, thank you.
Yeah, sorry about that. Yeah, so I'm going to be talking about a data set that was just released in June. And the project that we went through in, like it says here, defining and measuring the U.S. ocean economy. Oh, okay. So I have an overview section with a few slides that give some background on the project itself, and then I have a few slides talking about the methods and the data that we came up with. The project, this project, it's the ocean economy statistics. Its proper name is the Ocean Economy Satellite Account. It builds on decades of research by NOAA, by the Bureau of Economic Analysis, the Center for the Blue Economy out of Monterey, California, and a lot of others to define and measure the marine economy of the United States. NOAA and the Bureau of Economic Analysis began planning this project in 2011. It was not until 2017 that Congress directed NOAA to develop an ocean economy satellite account. This has nothing to do with actual satellites, physical satellites in the sky. It refers to the fact that the models that we use to generate these statistics are based on, but separate from, the data that are used by the Bureau of Economic Analysis to generate estimates of GDP. There are a lot of other countries around the world doing similar work, and we've been working closely with them to develop definitions and methods to yield results that can be compared internationally. So, two definitions here. Ocean dependency, we refer to this, a lot of countries call these data their ocean economy data, and for consistency with them, we use that same term, but it's in the United States, it's a little more complicated. A lot of marine activity takes place in other places. The definition of the marine economy that we used here is anything that takes place in the marine environment, things like marine transportation, things that use economic activities that use essential inputs from the marine environment, like seafood production, activities producing goods or services predominantly for use in the marine environment, like navigational equipment, and things that would not take place if it weren't located close to the coast, like the tourist-related beach rentals, that sort of thing. It gets a little trickier in the U.S. because of our geography in defining what is marine. We obviously include the oceans, but a lot of marine activity takes place in the Gulf of Mexico, Chesapeake Bay, Puget Sound. A lot of marine activities, marine transportation and coastal tourism that is very similar to what takes place on the oceans happens in the Great Lakes. And so we include the shoreline adjacent to these waters. Some of our shipping terminals, things as far upriver as Baton Rouge, Portland, Oregon, they are, pretty far inland, but we include that as part of the marine economy because of the function of providing international shipping. This is we've been developing data measuring the ocean economy for a number of years and disseminating those data, but this is the most accurate and comprehensive view of these activities so far. The existing data sets prior to the satellite account included 6 marine sectors. We include 10 here, and we have a much more accurate, it gives us tools to measure these sectors more accurately. The goal is to help businesses, policymakers, and making decisions and investing and hiring. It helps the public understand the importance of the ocean to the national economy, and maintaining these data sets over time will let us monitor trends and highlight emerging industries and show dependencies between the industries. We're targeting a pretty diverse audience. Federal and state agencies with management and regulatory responsibilities can see the economic importance of the industries that are affected by their actions and better understand the economic implications of those actions. Certainly, academic institutions can use the data for a wide range of research that would be valuable to NOAA and others, and it further advancing what we understand about the marine economy. Nonprofits and non-governmental organizations can use the data to demonstrate the economic importance of their activities, and the private sector, obviously, to support investment decisions, identify growth opportunities, and that sort of thing. So these are the 10 major sectors that we are measuring. We have fisheries and other bioproducts. That's commercial fishing, fish processing. It includes the emerging marine biopharmaceutical sector, marine research and education. That's something that we were not able to measure in past data sets. Professional business services, these are those services that support basically the other 9 sectors, and everything from engineering to maritime law, that sort of thing. This marine construction includes primarily dredging and coastal engineering, coastal habitat restoration, national defense and public administration. We do include the expenditures of government agencies in the management and performing science associated with the ocean environment. We also include the U.S. Navy in that sector and the Coast Guard. Offshore oil and gas, and that sector includes also other offshore mineral production, primarily sand and gravel, but it's dominated by oil and gas. Marine transportation, shipbuilding, which also includes ship repairs, and then tourism, recreation, and power generation. Right now, power generation is focused on the fossil fuel generation that has some dependency on the ocean for receiving fuels or using cooling water, that sort of thing. But as the alternative energy, the wind and wave and other energy sources in the ocean are beginning to be exploited, those will be included here. A little bit about the methodology and the results. We started, BEA has a very detailed accounting framework that they use to estimate gross domestic product. They have a what's called a supply use framework. It's a grid that shows who produces these different items that make up our economy, items being products or services, and then also who is using those items in the production of other goods and services. And it's very detailed. There's about 5,000 categories of goods and services. And so we started with those and did a lot of research to identify which ones contain activities that are ocean dependent. It doesn't mean that that entire category is ocean dependent, but it contains some significant amount of ocean dependent economic activity. And then for each one of those, we did a fair amount of research to develop coefficients that show the portion of that cell that is ocean dependent. And you can see here at the bottom, we used a lot of data sources from federal government data sources and also industry associations that provide data on their industries. So these are the results. These are prototype results that were released in June. The ocean economy represents about 1.8% of nominal GDP. That was in 2018. This seems like a small number, small fraction of total economy, but the US economy is very diverse. And this is fairly consistent with the ocean-based share of the total economy in large developed nations. In some places where you have a maybe an island nation or a small coastal nations, you'll see larger percentages of the total economy dependent on the ocean. But in countries like the United States, again, these large diverse economies, that's pretty typical. It's about $373 billion contributed to GDP. The gross output, which corresponds roughly to total production, or in the case of the government expenditures, total consumption is about a little over $600 billion. 162 billion in compensation, which is wages and other benefits, and 2.3 million employees. To put that 1.8% of our economy in perspective, you can see on the far right, this is the gross output associated with the US ocean economy. And what I've done here is compared it, did a little bit of cherry picking. I compared it to sectors that people intuitively know to be important. And you can see that this is larger. The contribution of the ocean to total gross output in the nation is larger than public utilities, larger than the agriculture sector, and then this data processing, internet publishing sector. They're all big, they're all important, but in this slide, and I do underscore, I've done some cherry picking to pick these sectors that people, again, intuitively know these are important sectors, and the ocean economy contributes more to gross output than these sectors. On the these are kind of comparisons. These are comparisons to the total economy of the United States, the growth from 2017, 2018, and I guess there's 3 points to emphasize here. The growth patterns in the ocean economy were pretty similar to those in the U.S. economy as a whole. In GDP and gross output, it was a little greater. In terms of compensation and employment, a little lower. But the ocean economy is like any other sector of the economy. It has some years that are better than others. We have broke down into these 10 sectors. You can see that the marine economy, and again, this is pretty consistent with what you see in other countries. It's dominated by tourism recreation and national defense and public administration. In the national defense and public administration, the Navy accounts for the largest share of that activity. Marine transportation is about 9%. Offshore oil and gas is about 13%. This is one of the sectors that, compared with the previous data sets, that we're able to develop much more refined estimates. The older estimates exaggerated the contribution of oil and gas in the offshore environment to the economy, primarily because of the very complex situation you get into in Harris County, Texas, Houston, the Houston area, where a lot of the international headquarters for oil and gas are located there. And so it was difficult using the previous methods to separate out these activities associated with the international headquarters from those associated with the production of oil and gas in the offshore environment. We released prototype statistics in June of 2020, and here is a link to the data and the documentation. Let me see if I can get out of this full screen mode, and I cannot. I'm not sure how to do that. I'm wanting to show you, but this is a link. This is a link to the website at BEA, where it includes the, you can download the entire data set, and you can, we have a methods paper that's located there as well. And we have an email address that goes to the entire team. If you have questions about the data or about the next steps, that sort of thing, you can send that to oceaneconomy@noaa.gov. And the efforts in the upcoming year, we've published the statistics, and an important purpose for publishing the prototype statistics is to get more input from researchers and from the industry to see if they, if they seem right, and if there are major problems, if they can identify data sources that can help us to improve those. Right now we have data for the national level only, and the data for the years 2014 to 2018 will be adding each year a new year of data, add the 2019 data in the coming year. And we don't yet have the real gross output, real GDP figures, and we'll be adding the inflation adjusted values for gross output and value added. And that is all. Again, this is the email address that you can use with any questions or requesting the data, but the data are available, and this is the link to the website at bea.gov, data, special topics, ocean economy.
All right, thank you so much, Jeff. A fascinating compilation there, and lots of amazing information that could be looked at over the years. Sounds really valuable. Okay, I think we have probably gone a little bit beyond where we should be, and I'd like to now introduce David Ryder from ICF. He's an economist at ICF in Fairfax, Virginia, and he will be talking on economic modeling of hazards in coastal systems. Thanks, David.
Good morning, everyone. Can you hear me?
Yeah.
Great. Thanks for that introduction. Again, my name is David Ryder. I'm an economist at ICF, and I have a background in resiliency and economic impact analysis. And today I'm going to talk to you a little bit about the data and the tools that I use in modeling the economic impacts of various hazards. So I've been looking at the presenters and the people who are attending this conference. It looks like a number of you are scientists or climate scientists or planners, and so you probably have a good idea of what these hazards are. But the several hazards that I work with the most are on this slide and arranged in my experience of which are sort of the easiest to the hardest to value the impacts of. So to go through these in a little bit of detail, the first hazard here that I work with is flooding. And this includes sort of sea level rise, storm surge impacts, king tide flooding, and it generally involves sort of property and infrastructure damages. And there's pretty good publicly available information for this hazard and the damages associated. We've got generally pretty good flood maps for coastal areas, although sometimes the flood maps are a little bit outdated. There's also a lot of historical data around various flooding impacts and the different flood intervals, whether it's 5-year, 10-year, 25-year storms. There's pretty good publicly available data for that. Next is hurricane-related impacts. These are obviously closely related to flooding in terms of storm surge, and there's generally a lot of good historical information available, although some of the values can be anecdotal, and sometimes you see infrastructure hardening investments and the various storm characteristics that can sort of complicate using historical data for forecasting analyses. And sometimes the wind damages can be tricky to assess without using some private damage models, although a number of these models exist, particularly for the insurance industry, and using those data can be particularly useful for forecasting models. Also do some work with modeling precipitation and the precipitation hazard and those impacts, both short and long-term impacts, looking at cloud bursts and that sort of thing. Typically, in my experience, this is very location specific. Our analyses tend to rely on sort of stormwater and runoff modeling, which can be needs to be extensive at times, and we need detailed data about what the stormwater management systems are in an area in order to be able to quantify and monetize various impacts. And finally, I work with heat wave hazards, both short and long term. These often involve health benefits, but can be difficult to assess sort of beyond using historical data sets. There are a number of benefits that I tend to look at for hazard mitigation listed here. The first and foremost is avoided physical damages. So this is often related to something like flooding. It involves looking at various flood maps and incorporating depth damage functions that relate your flood depths to property damages based on a number of, say, structural characteristics like first floor elevation and that sort of thing. Also do a lot of work around avoided emergency response costs and avoided loss of function impacts. And I generally combine these two impacts because they're pretty closely linked. These relate to various services or businesses that are disrupted as a result of, say, buildings being flooded or losing power or the road networks being interrupted. And so this often relates to value in terms of, say, willingness to pay for emergency services or sort of the lost revenue from various businesses. Other benefits include avoided injuries and casualties. This usually involves looking at historical data and anecdotal data and using something like the value of a statistical life or the value of casualties or the value of, say, hazard PTSD to sort of quantify and monetize those sorts of casualties and avoided casualties for inclusion in some sort of benefit cost analysis model. And then finally, also look at some societal and environmental benefits. These tend to be sort of indirect or co-benefits that may result from something like green infrastructure investments. So if you build, say, parks or sort of environmental or green flood walls or berms, you often get sort of co-benefits in terms of recreation or health benefits that are associated with those investments. And so when I do this analysis, when ICF does this analysis, we try and create practical set of results that decision makers can use in their planning process. And that idea really drives our work. And there are a number of tools that we use when we're looking at evaluating the various damages or the benefits of hazard mitigation. And one of the first questions that we have to ask is, how much data is available and what kind of data do we have? And there are a number of tools that I use to look at specifically damages, and the tools that I use the most are the two listed here. These both come from FEMA. There's the HASIS tool and then the FEMA Benefit Cost Analysis Toolkit. And they use similar but slightly different data sets. The HASIS tool actually uses GIS data, and so you can incorporate some of your physical data like your flood maps into the modeling. And it has a number of different modules. Actually, they both have a number of different modules depending on if you want to look at flooding or earthquakes or hurricanes. And the BCA toolkit actually looks at wildfire as well. And the BCA toolkit uses a slightly different method, and it is very sort of structure specific, looks at depth damage functions and the characteristics of the building, including first floor flood elevation, to calculate damages, and has some components that allow you to calculate loss of function and loss of emergency services into the analysis. These tools are generally pretty easy to use. They come with pretty detailed user manuals, which is definitely a plus when you're working with them. Another tool that we use in our analysis is hedonic analysis, and that can be used for estimating resiliency investment benefits. And often these are used to evaluate the benefit of non-market characteristics on market prices. So if you're looking at estimating the value of environmental attributes on housing price, this is the tool to use. So when you think about the value of a home, you can think about what makes up that value, and it's usually something like neighborhood or lot size or square footage, number of bedrooms, number of bathrooms, all those things you think about when looking at a home. But there are other environmental or resiliency benefits or attributes that can be used and sort of evaluated within the pricing data to try and assess what the market price of certain components are. And ICF recently conducted a hedonic analysis for the city of Miami Beach that was looking at the impacts of housing and roadway elevation on housing prices. And such analyses can really be used to help justify the public expenditures on flooding resiliency. So if you think about incorporating a flood wall or raising the elevation of structures or raising the elevation of roadways, that is going to obviously cost a fair amount of money, but will increase the prices of homes in areas where that's conducted. And so using hedonic analysis, you can tease out what the value will be for each homeowner and use that to help justify that spending. Hedonic analysis tends to require a pretty large data set and a detailed data set on home characteristics and prices to generate a robust model. And so it's definitely something that has a lot of data needs, but something that can be used to help justify expenditures. And then there are a couple of tools that I use a lot for estimating economic impacts. And these include IMPLAN and REMI. And IMPLAN is a local and regional level model that allows the users to generate industry level impacts using a series of industry multipliers. So I think in the last presentation, there was a lot of emphasis on different sectoral results. And in my work, we also focus on sort of which sectors in the economy are gaining and which sectors are sort of losing from various climate hazards or from infrastructure investments. And both IMPLAN and REMI let you do this in a fair amount of detail. IMPLAN has something like 500 sectors that you can input values into and export values out of for your analysis. And for each of these sectors, you can look at changes in employment or output or tax impacts. IMPLAN is a static model, and so it focuses on single year impacts, but does have a pretty detailed sectoral list that you can look at. Another tool that I use is REMI, and it's similar to IMPLAN, but it's a dynamic model. It has a little bit less sectoral or industry level detail But the beauty of REMI is it's dynamic, so that you can look at multiple years and have inputs into multiple years and sort of see how shocks to the economy result in various impacts across time. So you can think about, say, a hazard like a hurricane, and you have the initial flooding damages that are a negative input to the economy. There are then expenditures by, say, federal or state relief funds that are both sort of a positive impact, an influx of money to the economy, and maybe a long-term negative impact as that money has to be paid back. When you think about other impacts, there's that investment money that goes to the construction sector. So the construction sector tends to see a boom right after a hazard, but that money has to come from somewhere. So consumers will see maybe a long-term negative impact as they pay the money back. And so all of that can sort of be captured within REMI, see the fluctuations in the economy, and see sort of how fast the economy can recover from various investments or from various hazards through the investments that are there. And REMI is a very detailed tool. It allows you to play with employment, output, tax, price impacts, model the effects of various consumers or various commercial or industrial industries. And it outputs a lot of these different components as well to account for the fluctuations. Now, both of these models they don't natively use the physical data like flood maps that, say, some of your other vulnerability analyses or tools might use. So to input into these models, it does require transforming the data into damages first. The tools need something like investment dollars or employment numbers in order to sort of model the impacts. So there is some transforming of data that's required here, but the benefit is you get to output various value-added and input components in your results. And you can also look at the number of county level and region impacts. Both of these tools allow you to go down to the county level or aggregate counties up to the state level and sort of look at various leakages in terms of employment or investment leakages that might leave your immediate region. And then lastly, what I want to talk a little bit about are some of the cascading impacts. Generally, when we think about vulnerability or damage assessments, we tend to focus on the direct effects. We look at property damages, or the physical damages from something like flooding, but these initial impacts can have fairly substantial effects downstream. Services and businesses that may not be directly hit by the damages can still be subject to other vulnerable infrastructure. So you think about maybe transportation infrastructure, the roadway system, or the grid infrastructure. And if these components go down, even businesses or services that haven't been flooded or damaged are often impacted. So maybe there's a hospital or something, or emergency service that's elevated, but if the grid goes down or the roadway system goes down, they can't access the hospital, they can't get patients there. Often there are backup systems like generators, but that's a short-term fix as opposed to a sort of a long-term solution. And so it's important to think about some of these downstream impacts when we're looking at the impacts of various hazards. So I think I'll stop there and pass on to the next presenter. Thank you very much.
Thank you, David. Okay. So I guess we are at our last speaker for this segment. And so Jeff Chukowski is the director of the Center for Insurance Policy and Research at the National Association of Insurance Commissioners. And he will be speaking about understanding the economic impacts of flooding. Jeff, good to be in touch. It looks like maybe from what I'm seeing right now, it might be beneficial to not show your video. There's some strangeness going on.
I know. Can you hear me okay though, Mike?
Yeah, I'm just worried that the bandwidth might be too much or something.
No, Yeah, I can shut it off.
Okay.
It's probably, I mean, everyone's in just a little tiny block anyway, from what I can see on the screen.
Okay.
But could you see my slides?
Just a moment.
Yes, we can.
If you could switch to full slide view, that would be beneficial. Yep, there we go.
Better.
That's good. Thank you. And I guess we're ready.
Okay, so yeah, thanks for the introduction, Mike. And you know, I feel like from the last talk, I'll just kind of build off of that a little bit and provide a few sort of applications to some of what he was discussing. So here's just sort of a simple framework for thinking about valuing changes to the physical side. Here it's water system changes. So you have something that happens. It could be induced from sort of a water management plan or just some natural occurrence that's happening. And then you have these changes in water quantity or water quality. And as the last presenter was discussing, ultimately these impact sort of how that water is used. And that basis and understanding that change in that use, or what we call the service flow, allows for this valuation to happen. So you're starting to link the physical side to the economic side. And here's just a number of different examples, and some of these, a number of these have already been touched upon in the previous presentations. But the one that I'll speak to first is this notion of flood protection, and David was mentioning this in the last talk. You should have these avoided losses from having some notion of water supply impacting flooding in an area. And then there are a number of other uses that you can tie into, and we'll come back to some of these at the end in thinking about how you measure those. So this is, and actually, you know, in hearing some of the other talks, I mean, I feel like this hydroeconomic optimization framework, this HEO model, is sort of a nice way of capturing, combining the physical with the economic, with the social, behavioral. And, you know, Mike, you obviously have a lot of experience with this. So this was part of a WSC NSF grant that Mike Sukop was the co-PI on with Vic Engel, where they developed this HEO model for South Florida. And the idea here is with these HEO models is that you're, in this case, sort of pushing the water, whether it be surface or groundwater, to different parts of the landscape of the area. And here, this is all, a lot of it is very heavily managed in doing that. And by pushing areas and pushing water in one way, you are not pushing it somewhere else. You have these trade-offs that are occurring. And it could also be that you're pushing it too much in one way as well. And so the way that this is represented in these HEO models are through these penalty functions. So if you push too much water, which I'll go through here in a second, you could have a penalty associated with that due to flooding. If you push too little water in one way, you could have a penalty associated with that because you don't have enough uses for that, for households. And so for South Florida, and I'm sure this is probably similar in other coastal areas, you have these, you have a limited resource in terms of the water that's available, and you have a number of users that would like to have this water. Here was agriculture, urban, and then also the environment with the Everglades. And so as you're trying to manage this water flow and also potentially the water quality, or how those are connected, you have these trade-offs that are occurring between these different areas, and you can use economic analyses to sort of to help measure these. So part of my role in this project was to try to develop a penalty for too much water being pushed into an area. And so the way that we did this was to, as the last speaker was talking about, we looked at flood losses in South Florida, and then we wanted to relate sort of the physical side of that to those flood losses. So, and I believe Ali was mentioning this in his previous, in his talk too, where you have groundwater levels being maintained, and you want to have them high enough so that they're useful for the urban area, but if they're too high, it causes flooding potential, and then if they're too low, and Mike, you can help me out here on the physical side of it, you have these saltwater intrusion effects that happen. So you have to maintain it at a certain level, but by doing that, it induces the potential for more flood risk to occur. And so we modeled this in an area of Miami-Dade in 16 water management district watersheds, and we collected monthly data over about 15 years. And this monthly data, importantly, I think for the purposes of this workshop, incorporated the physical side where we were capturing groundwater levels. And we did this in sort of two different ways. We normalized them and had these standardized groundwater levels, and then we also took them in comparison to the mean depth level in the watershed. And then we simply ran a regression analysis on this where we were trying to get a count of flood claims incurred in these water management districts, importantly as a function of the physical aspect, the groundwater levels, and then controlling for a number of different things, some of which were physical as well, such as rainfall amounts. And so when you do this, what you can do, and this sort of takes the shape of what a penalty function could look like. So as you go off to the right on your x-axis, as the groundwater levels are higher than these long-term means, you have a penalty associated with that for having too much water in the area in terms of flood that are occurring. And so again, we modeled this in terms of the actual flood losses that had happened from a historical perspective, and try to have this relationship there to ultimately lead into the penalty function for the HEO model. And it was incorporated in that. So another way to think about this too, though, and this also ties into the last talk, is you want to avoid having too much water in an area. So what often happens in South Florida is that water is discharged out to the coast, and it doesn't make its way through the system, or it's discharged in other ways. But we were looking at the water level in Lake Okeechobee and having those discharged off to the coast. And so this graphic here depicts that, where you have water levels prescribed within the lake, and you don't want them to get too high, because then what ends up happening is there's a flood risk for areas that around the lake, including agricultural areas, but also the urban areas that are there. So the water is pushed off to the coast, and then as our speaker was alluding to earlier, you have these algal blooms that happen. And from David's talk, you can sort of associate these through hedonic analysis. So if you look at the house in the lower right-hand corner, ideally people wouldn't want to be living somewhere on the water where they have this in their view, or there's a smell associated with that. And so you try to find the difference between that home and another similar home where they don't have these water quality impacts happening, and that gives you your additional benefit for clean water. So, and was mentioned, this is called hedonic analyses, and there have been a number of papers published in this area, but some specifically down in South Florida. And again, kind of linking this back to the physical side, you need to make sure that you're incorporating the water flow data that's coming from the lake through the various canal systems, and then translating that into a value that you can use within your hedonic regressions. And we're also incorporating, translating this into water quality values as well. So we're trying to highlight the flow values, but also the water qualities. And there's a lot of water quality stations and monitoring in South Florida. And then you can see all the home sales is represented by the black marks here. And so you're trying to capture these home sales as a function of the water flows, as a function of the water quality and the interaction of those two things. And then ultimately that leads to you to be able to infer some economic value of improved water quality. So the last slide that I have, Obi had asked to kind of think about some challenges and gaps. And so, I feel that, one thing is certainly, this takes, one of the beauties of, of the project that Mike was running, was that it was interdisciplinary in nature, and they had organized it that way. But, you have to talk amongst the disciplines and make sure that what you're measuring on one side is able to fit into another. And some of these things are rather difficult to measure too. And what time scale do you want to have them at? So it's just trying to properly account for the data in that sense and linking them together, whether that be on the hazard or the exposure side. There's flood claim data that's available, but there was some conversation on the chat. There's some privacy concerns around some of that too. How do you know you have good exposure data for the area? Another big piece, though, is this table here directs sort of a schematic of how to think about these various values, and they're really split. You can think of this as more of a 2x2, direct and indirect, and tangible and intangible going across the top. And really, what we were measuring in the flood piece were direct sort of insured losses. But if you come back to the social vulnerability talks at the beginning, a lot of impacts are especially direct. People don't have insurance due to these social vulnerable populations, and so there's a missing piece here in terms of the actual losses associated with some of these things. And then you have these indirect values that happen, and the hedonic analysis starts to get at some of that, but it's really more of a tangible indirect value that has some market value, associated with that in some way in terms of inferring that from housing. But oftentimes what you find is that these indirect losses, especially say for hazards in particular, they're not very well understood. They're not captured very much. These take a long time typically to kind of come into fruition, and they're not tracked as well. I think some of the models that the previous speaker was talking about can get at those, but these are they're relatively complex models. And so it's trying to address the values across these different types of pieces is, I think, a real challenge and also a gap. And then I did enjoy the the behavioral talks too. And another nice thing with the HEO models is that you can build in sort of social and behavioral systems into them as well. And in fact, we had done that in the project. So that was the last slide, and I'll leave it there. Thank you.
Well, thank you very much, Jeff. So I think this is, this concludes this section. I think we're a little bit behind schedule still. I'll turn it to Obi to see how he wants to proceed, I guess.
Yeah, so we are about, we don't have the time that we had for Q&A anymore, but we have two choices: either have some Q&A and then catch up during the lunch hour. We have some slack there to keep session 3 on track. Are there any questions? I don't see any questions on the chat box, so what I asked originally was to put a Q and a question mark if you had a question. Since I don't see one yet, Why don't we go ahead with the session 3 that Tiffany and Sparkle are moderating. We only have 3 talks. So right after lunch, we can pick up the Q&A. How is that?
Yeah, let's go. Are we ready? Carl Goodman, thanks for joining us today. So Carl is the director of the Integrated Ocean Observing Systems program, and he's going to be talking to us about biological observations and models. Thank you.
You're welcome. I'm trying to go to full screen. I don't think I'm quite there yet. And Tiffany, can you hear me all right?
Yeah, sounds good. Thank you.
All right. Thank you for having me. I color outside of the lines sometimes, so my talk was on the agenda, said biological observations and models. I'm using a little creativity. I'm going to try to cover coast people observation, science, and technology, a bit of a bigger picture, and explain to you all the structure of the Integrated Ocean Observing System. I'm really glad to be a part of the CoPe workshop, and the NSF funding that's coming along for this important research and development activities, I think will be a great benefit to the nation. And these talks today have been wonderful to hear so far. And then I'm followed by 2 of the IU's regional experts, one from the Southeast and one from the Northeast. So without further ado, I'll move forward. If I can drive. Yeah, sorry. All right, so the IUS was established by law in 2009. We have 7 societal benefits that are lumped into these 4 mission areas here: predicting weather and climate variability, safe and efficient transportation and commerce, risk reduction for coastal communities, and healthy ecosystems and water quality. And within IUS, we do a lot of work to try to apply data, models, and information to problems of the day to support decision making. The program is set up in a regional to national to global scale. At the regional level, we have 11 IUS regional associations. They're all certified by NOAA for the purposes of data management. They're stakeholder-driven, science-based, and policy neutral. The task of the regions is to meet the highest priority regional needs, nest those into a national system. At the national level, our job is to integrate ocean, coastal, Great Lakes data from all of the federal agencies that might be gathering data in those areas, make those data available as universally and easily as possible, and make those data also integrated with the global system as well. This is a diagram that Melissa Iwamoto, the director of the Pacific Islands region, presented at Ocean Obs 19. And it is just meant to show you that within IUS, we take data, we make sure it gets where it needs to go, we deliver it in information products and services, and we work with the community. And we repeat the process annually, an ongoing basis, to iterate with stakeholders to make sure that what we're providing in terms of information and decision support is useful, is applied to the right problems on the right timescales. And so it's that ongoing stakeholder engagement that is really the strength of the IUS regions within the United States, and understanding the gaps and needs of our communities at the coast. This is a bit of an eye chart. I'm just showing you that we do have a list of core variables within IUS. We're trying to standardize the way that we collect these as much as possible, standardize the way we handle and manage them, and apply them to decision support and services for communities. Within IUS, we have 2 program elements that are not just observing, but ocean technology transition projects are designed to transition new technologies into operations, sort of the higher technology readiness levels into operational systems. And we have lots of projects ongoing. 6 new ones were just announced. So check that out on our website if you're interested. We also have a coastal ocean modeling test bed, which is run through NOAA. And within that, we have extramural partners adding modeling capability into the national system. We run a series of projects every 3 years and new funding opportunities every 3 years. We will be putting an announcement out later this winter for the next year to start a set of new projects as well. And the players within the CompT projects are also participating in the National Water Initiative Coastal Coupling Community of Practice, which is designed to bring the community of ocean and coastal modelers together with the national water model experts to share expertise and best practices and advance our capabilities together. And then finally, I'm going to go through a few products that our office helps develop that are tools that enable anyone to get access to information. So we have a model viewer. We call it the EDS model viewer. That stands for Environmental Data Server. It is designed to show model outputs that are available in space and time. So if you go to a specific part of the map, you can see on the left side all of the models that we have available so that you can compare different model outputs. You can drop a virtual buoy and get a graph of the different models. You can also do that near a real-time asset, which are also displayed and available in some of the instances on the map, so you can compare real data to the model outputs. So that's a tool that we make available to the community and try to maximize its utility over time and increase functionality and add version features as we go. Additionally, we have an environmental sensor map, which is designed to show you any data available within sort of near real time. In the last 4 hours, anything that's live and available is available on that sensor map, and that middle website address there will get you to that. This slide here is also showing you that we're doing a big release in October where we're going to make sure that all of the National Science Foundation's Ocean Observatories Initiative data are also available via that same tool. And it's good to be working together to make sure that those data are interoperable. We also do work with biological data, despite my changing the title of my talk. We have a whole set of marine biodiversity observation network projects, and we are working with sanctuaries and the Integrated Ecosystem Assessment Program within NOAA and the National Centers for Coastal Ocean Science to figure out new ways to display those data on web-based protocols and provide them as condition reports for the marine sanctuaries. So the sanctuaries are a customer for those types of data, and they have customers that need it in easy to use, understandable formats. And we've been doing that. Webinization is one of the words we use for taking that data and making it available on the web. And then the way IUSE works is we've got this regional construct fitting into the national and global at the bottom left. We build communities around specialty areas. So whether it be harmful algal blooms or animal tagging or marine biodiversity, and we try to establish best practices. We write things down if we know standard procedures that are available, best practices in terms of quality assurance and real-time data. We have manuals for that. We work across to build partnerships, and we try to advance technologies and infuse new research and development capabilities and science into the system as we go. And I've moved my up. And so with that, I'm going to save you some time and get us back on track a little bit. With all of these human dimensions briefings today, I grabbed this Gary Larson Far Side comic and put it on my slides because I couldn't resist. It made me, for some reason today, think about it. And I will stop there and see if there are any questions.
Thank you so much, Carl. Any questions? So Carl, what would you say would be sort of the biggest challenge in terms of interoperability across these different, data types and data sets that you all are working well to integrate?
Answering that question all of a sudden made me thinking about that question. It depends, I guess, on the data types you're talking about. And so the level of maturity of our understanding and use of the different data. So physical data types that are a little more understood because we've been dealing with them longer are a little more easy to work with and create interoperable standards. data types such as sound and using acoustic backscatter data, and deriving information from those data. That's some of the newer data types we're having, which can be really large. And if you want to manage them and handle them, we're trying to figure out how do you get the snippet of information from a big data set like that that's useful, that can support decisions. So if you've got presence, absence of marine mammals, can you do edge processing at the sensor to potentially give you the positives of presence, absence of a marine mammal, and just use that data if that's all you're interested in, for instance. So I kind of dove into a small scale answer to that problem. And we often solve these problems by bringing folks together, science and technical experts, via workshops to resolve questions of the day and advance our understanding of a given domain that we might be working on.
Great, Carl. That reminds me of Ali Mustastavi's approach that he's been using. So great. So let's go to the next talk then. Thanks again, Carl. Deborah Hernandez from Executive Director at the Southeast Coastal Ocean Observing Regional Association. Thank you, Deborah.
Thanks, Tiffany. Can you hear me all right?
Yeah.
Great. And can you see my screen?
Yes, we can.
Cool. Well, hello, everybody. Thanks, Obe, Tiffany, and the rest of your team for the invitation to join today. I've been learning a lot. I'm talking about opportunities and innovations in monitoring for improving coastal hazards resilience. And my perspective is that of a program manager, not a modeler, but I hope to highlight some opportunities to partner to improve hazard resilience, primarily in the biophysical space. So let me figure out how to advance my slides. So I'll begin by providing a quick overview of the Southeast Coastal Ocean Observing Regional Association, including our expertise in data management, highlight some key elements of our regional observing plan, discuss relevant ongoing work, and conclude with my perspective on some opportunities to partner on observing and modeling to address coastal resilience. So Carl did an excellent job of discussing the greater IU's enterprise. I'm going to provide insights from the perspective of one of the regional associations. You'll hear from my colleague, Tom Shaika, shortly, who will do something similar. While all the RAs are somewhat unique, we do share common capabilities. So if you hear something of interest to you from me or Tom, keep in mind that there are other RAs, if your interest is in a geography other than Southeast or the Northeast, that you might want to think about collaborating with. Socorro's domain extends from the West Florida Shelf around to the border between North Carolina and Virginia. Our internal team members sit in St. Pete, Florida, Wilmington, North Carolina, and my home, Charleston, South Carolina. Our board is elected from our members, which include academic institutions, private companies, primarily sensor companies, federal, state, and local government agencies, and other nonprofits and regional organizations from the Southeast and beyond. When I discuss Socorro's work, I want to be really clear that I'm discussing the work that we do collectively via our members and our funded partners. This is a quick snapshot of our strategic plan. You can find it on our website. I want to highlight two things. The first is the word partnership, which is a key tenet of our work. It's part of our mission, one of our core values, and also one of our strategic goals, as you'll see highlighted in the gold underline. The second thing I'd like to highlight is this strategic goal that calls for utilization of a prioritized and science-justified ocean observing system plan. I'm going to talk in a little more detail about the plan, but here I wanted to clarify that this is a system plan. It's not just about observations, but also includes monitoring, data management, product development, and education and outreach. So where does Socorro direct our funding? The lion's share does go to collecting observations, anywhere from 55 to 65% of our annual budget. We support sustained observations using a variety of sensors. Some of them have 15 to 20-year records at this point. Our data management system is certified by NOAA as meeting federal standards. Observations are used to support models and other products that meet the needs of our stakeholder communities, which again, Carl highlighted, and which also fill gaps in observations. You can't observe everywhere, so the models are critical integrating and data gap filling component of what we do. And of course, we also conduct some education and outreach activities to make sure we're connecting with the next generation of scientists. I'd like to draw your attention to our data management capabilities. Carl highlighted that as well. They're a result of over a decade of investment in data management communication. Socorro, IUs, and the other RAs have significant expertise in this area. We all have regional level data portals or data aggregation centers. We also feed the data up and down, both to federal level users and into specific web applications for local stakeholders. We ensure the data is appropriate, has appropriate metadata and QA/QC before moving that data out of our system, and it is used for a variety of purposes, including feeding national forecasting models, as well as search and rescue, among other uses. The data standards and QA/QC procedures are ones that are community developed and regularly updated. We also address issues of interoperability by making data available in a variety of formats. I'm going to switch gears and talk a moment about our regional coastal ocean observing system plan. This plan was vetted with stakeholders throughout the region, as well as Socorro Science Advisory Committee and our board. We are using it to make decisions about funding priorities for the next 5 years. So if you want to know more about where we're headed, I would direct you to that plan. Of relevance to today's workshop is a section on coastal flooding and sea level rise, and there's a link to that document in this slide. As part of the plan, we highlighted challenges, and one of the main challenges in addressing coastal flooding at the local scale is meeting the demand for street level flooding data. That's been mentioned already today. There are additional challenges in data collection and modeling that are noted as part of our plan. The plan also identifies where we're currently making investments. Obviously, with the collection of real-time data in the coast and ocean, we also invest in web cameras. I'll give you a little more information on that in some of our modeling work in a moment. We're hosting a middle school curriculum around sea level that may be of interest to some in this audience. And we're also the administrative home of the Southeastern Caribbean Disaster Resilience Partnership, which is always happy to welcome new members, as is Socorro. So I'd invite you to check that out as well on our website. The sort of final section of our plan that I want to mention is, again, the looking forward piece. We identified priorities for future investment, including partnering with communities to install low-cost water level sensors and incorporating ecosystem components into water level models, which again has been discussed briefly already today. And I'm going to move now to a couple of ongoing projects. Carl mentioned the Coastal Ocean Modeling Test Bed. Funding via IUs is awarded competitively, and Socorro partnered with Roy He and his team from North Carolina State University to do some modeling work that's built upon an existing three-dimensional baroclinic Northwest Atlantic Regional Ocean Prediction System, which is a mouthful. That larger regional modeling effort's been supported by Socorro for over a decade now. This new model will include new multi-scale two-way nesting capability to deliver high resolution and fidelity to link the ocean with the rivers. So it's a 3-level nested model. The highest resolution model is about 160-meter resolution. We're working in 2 watersheds. The St. Johns River model is pictured here with some test data from Hurricane Matthew. You see outputs from left to right of surface elevation, temperature, and salinity. We're about halfway through this project, and what we're working toward is to enable a transition from the research space to hopefully NOAA and some other operational users to have a new capability and improved forecast ability in these 2 watersheds. This next project I'm going to discuss is a new award we're really excited about through the Ocean Technology Transfer program, which Carl also mentioned. We're transitioning, a successful pilot project, the webcam applications testbed, to sustained network. So webcam data has demonstrated value to address significant gaps in our ability to monitor and accurately forecast various weather, ocean, ecological, and public health hazards. We're working to build an operational framework that can enable these relatively low-cost sensors to be utilized in both quantitative and qualitative ways to meet needs for increased observations. And we're also hoping to build a similar framework in the near future with low-cost water level sensor data. So more on that in the next couple of years. So in closing, I want to highlight a few gaps and challenges as well as opportunities from my perspective. First, we continue to see gaps in data, in observations, in having standards and metadata that enable broad use of data that's being collected, and in knowing how to easily find data. There are a lot of people doing great work, and unfortunately, it can be very challenging to access that data at times. Another challenge is in the modeling space. While we work with users regularly, requirements evolve over time, and it seems like no matter how well you think a model is at forecasting the information that users want, they often want it at a higher resolution and in different formats than you may have envisioned. So as has been mentioned, that interaction and iteration with stakeholders is really critical and remains a challenge. And then coupling between hydrodynamic and riverine or some of the social models and economic models to the biogeophysical ones, I think remains a significant challenge. There are also opportunities. The cost of sensors continues to go down. They're more disposable, more accessible to broader user groups. I think there are opportunities in developing data standards that are driven by the community and can enable broader use and access of data. And then I also think one of the things that organizations like Socorro can bring to the community are these data management capabilities, both by having data assembly centers and the expertise to help people put their data and format their data in a way that makes it more usable. And then I'll close by saying we're very interested in partnering with the folks who are participating in this workshop who are interested in tackling issues around coastal resilience. And I think I speak for my colleagues throughout the IU's program when I say that. So thanks again for the invitation to be here. And I'll conclude by turning it back to you, Tiffany.
Thank you. Thank you so much, Deborah. We do have one quick question for you. To what extent do you try to integrate citizen science into the webcam monitoring?
We are not doing it yet. This webcam project that we literally just got notice we were awarded of last week is going to build a framework that'll allow folks to upload video, for example, and we're working to make completing the metadata easy so that that data can then be utilized for different purposes. So it's an area where we're actively looking to do more work. And so if the person with the question wants to contact me to follow up, I'd be happy to provide more detail.
Yep, great. Okay, so we should probably get to the next talk then. Thank you so much, Deborah, again, for being here and telling us about Socorro. Our last talk of this session is Tom Shaika. He's the Product and Engagement Manager for the Northeastern Regional Association of Coastal Ocean Observing Systems. Tom?
Hello. Yeah, hello.
Hey.
How's my audio?
It's good.
Okay, now I got to share screen. Okay. And, no, I'm getting the open systems preferences now too. This is, and we use GoToMeeting. It's our, wait, let me try not now and just see if it shares. Nope. Okay, how about so I just send you the presentation if that's okay?
Yeah, you can send it to me, Tom, if you want.
Okay, sorry. Okay. I'm sorry, who am I sending it to?
So it's Maria Pulido. So it's MPULIDO.
MPULIDO. Okay.
At FIU.edu.
FIU.
Okay. And just to clarify, Tom, that's D, not a T. I thought perhaps I heard you say T.
I did say. Okay, thank you.
Okay.
Tom, this is Carl. I just hit send on an email to you and Maria, so you can reply all to that if you want.
Okay, thank you. Thank you, yeah. Thanks, Carl.
Okay. Deborah, are you still here while while Tom gets his slides up? We had one other question if you were interested in.
Yes, I'm still here.
Yeah, great. We also had a question about the community-driven data standards. What your approach was to that, and what things you're learning from that activity.
So Carl could back me up, but the IU's community has done a great deal of work around physical biogeochemical data, and they have a process called CORTOD, which is related specifically to real-time data. And the IU's program office generally supports a contractor to lead the effort, but experts in particular sensor technologies are invited to help develop the standards, and then they're vetted via a steering team, then through the larger ocean observing community. So that same approach is used for biological data. Carl mentioned acoustics, which is a little more challenging, but the methods and process are pretty standard at this point. And hopefully that answers the question. But the idea is to bring together experts on whatever the variable is, the parameter is, to do an initial sort of draft of what the standards are, to comb through literature and international standards, for example. And then once that draft's pulled together, to push it out to the community for review. So it generally takes some time, a year or so, to publish new standards. But when they are published, there's pretty broad support for the standard.
Great, thank you.
So the email I sent Maria, have you received it? I'm sorry, it's going to give you a Google
Yes, I
Docs
just
link
got
because
some
it's good.
sharing my screen.
Okay, so again, yeah, this is Tom Scheiker from Syracuse. I'm the product and engagement manager. And so I kind of work in trying to bridge that gap that I think it was Sam or some other presentations talked about between the researchers, the modelers, and the stakeholders. So what I'm going to do today is give you an overview of a coastal ocean forecast system, a regional coastal ocean forecast system. And I knew that Carl and Deborah were going to cover IUCE and what a regional association is. So I really appreciate that. So I was able to skip that information. And I just wanted to recognize that the NECOFS was developed for Syracuse by Changshen Chen of UMass Dartmouth and Robert Beardsley of the Woods Hole Oceanographic Institution. And throughout this presentation, you'll see that I'm going to be echoing a lot of themes that you've heard in some of the IUCE presentations and other presentations as well. So next slide, please. The region that Syracuse does its observing and modeling in is covered up by this significant low pressure system. This is a nor'easter, I believe it's from March 2018. So in the Northeast, we get to experience hurricanes sometimes, but more frequently it's these extratropical storms, these nor'easters, which can really be cause significant damage because they can persist for multiple days. So the coastline can experience surge, wave run up over multiple tidal cycles. Next slide, please. So hurricanes, these nor'easters, are significant coastal hazards for the Northeast, and there are significant areas of the Northeast coastline which are extremely vulnerable to storm-generated inundation. And also, the projections for sea level rise suggest that the impact from these storms may be more frequent and larger in magnitude. So those are the drivers for why Syracuse has been supporting the development and operations of a regional ocean forecast system. Next slide, please. And as you heard from the IUCE presentations and other presentations, engagement of stakeholders is really important. That's foundational to what we do in IUCE, trying to engage them early and often throughout the process. So in terms of the development and operations of NECOF, some of the key stakeholders that we work with are the forecasters in the regional weather forecast offices, coastal zone managers, state and local emergency managers, as well as the U.S. Coast Guard. Next slide, please. So I want to give you a little more detail on NECOFS. It is an integrated ocean atmosphere model system, which includes several subdomains, which I'll highlight. On a daily basis, it produces a 3 to 5 day forecast, depending on the forecast product. NECOFS is also used to develop a 30+ year hindcast or climatology, which was a need identified by the coastal planning community. And NECOFS is also an adaptable regional modeling framework. So NECOFS is being used to support the development of biogeochemical modeling, for example, as well as it has been used to model the potential impacts of a wind farm in the Northeast region. Next slide, please. So again, here's a illustration of the NECOFS system, which includes a regional weather model, WRF, and a regional hydrodynamic model, FVCOM. Both of those models, modeling systems include assimilation of satellite data and buoy data, so observations, some that we support, some supported by others in the region. NECOFS also includes a surface wave model. And as you can see at the bottom, there are these high resolution storm surge or inundation models. And the location of these models were identified through work with key stakeholders. These are areas that are highly susceptible to damage and flooding during these coastal storms. Next slide, please. So here, again, you can see the NECOFS hydrodynamic domain in the middle. That's that black grid. And the red arrows pointing down to these higher resolution inundation models, which include wave current interaction. Again, for the areas that are highly susceptible to flooding. And these high resolution models also include land, so they can show where inundation or flooding may occur. Next slide, please. So we have the modeling system running on a daily basis, producing 3 to 5 day hourly forecasts. And again, a key thing for IUCE is data standards and accessibility. So the output from these models is in a standardized file format and is made available through this Threads data server. So having the standardized model formats, the standardized system for access to the data really increases the accessibility and improves the use and interoperability of the output from this modeling system. Next slide, please. The NECOFS also includes a visualization tools, and here you can see visualization of forecasted inundation in a couple of areas in the Northeast, and this was for one of those extratropical storms. Next slide, please. Also, you can view the forecasts and compare them to actual observations. So on the left, you can see in black lines is the model predictions compared to observations from a buoy. On the right side, again, you have model observations compared to observations from a tide gauge. Next slide, please. So you heard a lot of detail, or some detail, about this tool that IUCE has developed, this EDS model viewer, which includes NECOFS. It also includes models from a lot of the other regional associations, as well as federal models. So again, this tool, you can visualize the model output, and also it has a capability of comparing models to each other. So these are important tools provided both at the regional level and at the national level as well. And just want to go back to those data standards. It's the implementation of those data standards that allow tools like this that can integrate model output and observations from a variety of sources. So next slide, please. And NERACOOS is also involved in a coastal and ocean modeling testbed project that both Carl and Deborah talked about. And so the project that we're involved in is working on coupling the hydrodynamic model. So that's, again, the black grid that you see on the map to the right, with hydrologic models. And the hydrologic models that we're working with are NOAA's National Water Model, as well as a regional hydrologic model. It's the UNH Water Balance Model. And the focus of the work is to improve inundation predictions along the coast. But this modeling system starts to get at that modeling system that I think it was Todd said would be needed, to predict that fish kill in Biscayne Bay. We have both a hydrodynamic model and you have a hydrologic model that's providing, input from surface water and groundwater, and it could include nutrients and so on and so forth. So again, we're developing that system through this CompT project. Another component of this CompT project is also the transitioning of components of the FBCOM model and NECOFS to NOAA for operational use. And again, as was highlighted in Carl's talk, through this coastal modeling coupling project, we're participating in this coastal coupling community of practice. There's the website there, and that's been a really beneficial effort to advance and learn about the challenges, of coupling these models, but also discuss, the challenges of understanding stakeholder decision-making processes and how to better deliver the information, whether it's from observations or from the models to stakeholders. Next slide, please. Also, NECOFS, is being used to develop forecasts for more of the planning time frame. So this NECOFS has been used to predict what coastal inundation would look like under certain storm situations under different climate change scenarios. So here you see Boston, the Boston area, and the predictions of inundation from an extratropical storm under different sea level rise scenarios. So again, this regional coastal modeling framework really allows us to deliver information both at the operational timescales and at the planning timescales as well. Next slide. So we've certainly faced, a variety of challenges this work, and I think you've heard many of these from some of the other presentations. So observations are really critical for these modeling efforts to validate, to verify the models. And then we certainly have challenges to some degree sustaining some of the observations we have, but we hear from the modeling teams that there are more observations that are needed. So there's a challenge to expand that. Data standard adoption is a challenge. Now within the IOS community, I think we've done a pretty good job, as you've heard from Carl and Deborah, about identifying and adopting data standards, which really supports interoperability and accessibility. But there are a lot of other data sources that are out there that would be really valuable to bring into these systems. But there are challenges to getting whether it's a citizen science group or even a state government to adopt some of these data standards that will increase accessibility, increase interoperability. One of the challenges for NECOFS that we're working on through the CoPe project is improving the technique for the prediction of coastal inundation due to wave run-up induced splashing or overtopping. And again, another challenge that I think we've heard before is understanding stakeholders' decision-making process and needs. That's something we're working on, but that is definitely a challenge for us. Also ultimately improving the delivery of products and services for stakeholders. Next slide, please. So some key takeaways from this presentation are it's important to start with stakeholders and continue to engage them throughout the process of developing, evolving, and maintaining these modeling efforts or observing efforts. Data standards are really critical to increasing accessibility, interoperability, and use of the models or the data from these observing modeling systems. And then sharing information, I put that in there kind of in a broad sense, whether that's sharing the data or the models, or sharing information like this. I've really appreciated this workshop and have learned a lot so far, and other efforts like the Coastal Coupling Community of Practice Group really highlights how beneficial these efforts can be in terms of sharing techniques, technologies, and best practices. And with that, I think we can go to my final slide. Thank you. If there's time, I'm happy to take any questions, but there's my email address for anybody who would like to follow up.
Thank you so much, Tom. Any quick questions for Tom? Okay, well, this gets us closer to back on time. Obi, you want to take it away? Thanks again, Tom.
You're welcome. Thank you.
Yeah, thank you. That's great. I mean, congratulations, you got back on time. So I'm sure everybody's hungry. So why don't we take the lunch break, because I don't see any other questions on the chat box. But we do have 15 minutes right after lunch. So why don't we take the lunch break now and then come back at 1 o'clock, and we can cover some of the questions if you have any. Otherwise, we'll get back on the schedule and have another set of 7 or 6 presentations that are covering the biophysical observations and modeling sessions. So thank you. Thanks, everybody, and hope you will all come back. I can see everybody still staying around for most part. So let's take the break and we'll reconvene at 1 o'clock. I think Sparkle is taking over as a moderator, right, Tiffany? Is Sparkle?
Yes, she is. Yep.
Okay, all right. We'll see you all at 1 o'clock.